at the Visual Computing Group (VICO) led by Dr. Hakan Bilen at University of Edinburgh. He did his PhD at Indian Institute of Science, Bangalore, where he was advised by Professor R. Venkatesh Babu. His thesis won IUPRAI Best Doctoral Dissertation Award and the SPCOM Best Doctoral Dissertation Award for year 2018. He did his master's at the Indian Institute of Technology, Kharagpur. My team and I are so lucky, sir, to have you as a resource person like you participating in lecture. Your presence and experience gave us more information for us. Thank you, sir. Thank you.
Thanks for a kind introduction. Thank you very much. I'm pleased to join you all in sharing some of the recent work we have been doing. So I can proceed, right? I can start sharing the screen and we can start discussion. Okay, thank you. I hope you can see the presentation. So yeah, I would like to make this as an interaction session. So feel free in case you have any doubts, in case you want to ask something. Yeah, you don't need to wait until the end of presentation. So at any point in time, you can interrupt me via audio or raise hands, whatever way possible. I will stop and we can discuss. Right. So today we'll discuss about intelligent machines and some of the ways in which we can fool them intentionally or unintentionally. So as Ms. Jahanvi was saying, I'm currently a faculty member, a visiting faculty member at the Department of Computer Science at IIT Tirupati. So the presentation includes my work from PhD days, although I've been continuing in this research area. Yeah, so in case the audio is not clear, anything, okay, feel free to stop me at any point in time. It is just an interaction, okay? All right. So this is the time of AI. We have seen a lot of success stories. We have been experiencing, not just seen, a lot of success stories of AI, right? We all have at least once said hello, okay Google in our smartphone. Some of you might be using Alexa. I've recently bought one Alexa for myself. I can tell a lot of stuff and it can understand. It can plan events. It can access my calendar and let me know what I have for today or this week or this month. Or I can add events. It can understand my mood. It can play songs according to my mood. A lot of success has been already being experienced in AI, right? Natural language processing, computer vision, speech and audio. These are the premier application fronts of artificial intelligence, right? These are very effective ways one can experience artificial intelligence, right? For example, if you visit places like China, you don't generally speak their language, right? So an application where you speak in English and that translates live into Chinese language is very helpful, very handy. It can erase the boundaries. Now you can travel anywhere in the world, right? Think of a speaker where people like Narendra Modi, they can speak in Hindi and parts of southern India can translate live into Dravidian languages like Telugu, Tamil, whatever language he wants to, right? These are very potential applications and they can bring in, as you can understand, significant changes. Computer vision is also another application front. A lot of influential applications have been put into real world, right? Driverless cars is something of very loved projects by different countries and companies, and you can see a lot of fiction stories come into real life, right? So the gist is today artificial intelligence is going to make lot of time and space with human interaction, right? So we are going to get a lot of tasks done by AI, right? For example, I've been banking with ICICI for quite some time now. So customer care uses a chatbot. So there is a robot, a chat robot, answering, listening to our queries in text, and trying to guide us how to resolve them, right? And pretty soon we will be deploying robo maids, right? Robo maids in our homes to take care of the daily chores, cleaning the room, or cooking, or serving, or take care of the children. So these are all not far away. They are going to be happening pretty soon. Some of the countries already we have seen things like this are happening, but it will happen more and more. For example, if you apply for a loan in a bank, I'm pretty sure there will be a robot, an AI, analyzing your data and deciding whether to give a loan or not, right? Yes. So the bottom line is, a lot of our decisions, a lot of our life activities are closely associated with AI, right? So a lot of these applications that are successful are driven by deep neural networks. At least, recently, at this point in time, it is true that most of these applications are driven by deep learning, which is deep neural networks are the models analyzing the data and taking decisions for us. So just, what is the bigger picture? So to understand the bigger context of AI, machine learning, and deep learning, this is how they span. So, right. So I hope you can see the arrow. Yeah, basically a bigger circle, outside circle is the AI. AI is general artificial intelligence, which involves a lot of activities, rationality, trying to achieve the human level intelligence, all that. So machine learning is a subset of tools to achieve some of those tasks. And within that, deep learning is another subset of machine learning tools that uses neural networks, deep neural networks, layers of neural networks. When you train to perform some task, it is called deep learning. So machine learning is some set of tools that can realize AI to some extent, and within that, deep learning is a sub task, sub tool, which involves neural networks, right? So this is where a lot of AI is very active at this point in time. A lot of AI tasks are being developed by deep learning at this point in time. All right. So what has changed? Deep learning is very young. Um, Let me say it's less than 15 years old. Um, Predominantly, the previous 7 years, 2014, is the breakthrough for deep learning. So one of the PhD students in Canada, University of Toronto, started applying in convolutional neural networks, and everybody in the world started looking at it. Yes, it can do a lot of tasks, and now 7 years later, everything is done by deep neural networks. All right. So what has changed before and after deep neural networks is this. So before deep neural networks, machine learning was there. It was 6-7 decades old already. So what was happening is, given a task of object recognition, so computer vision is, I'll make it as one of the applications to explain a lot of concepts. Although these concepts will be pretty applicable to other applications like speech and language also. But because I've been working in computer vision laboratories for some time, so all my applications will be computer vision. So basically, computer vision, you can understand, applying vision or giving vision to a machine. So whatever we can do with our vision, looking at the world, understanding what are the objects, and boundaries, segmenting, instance segmentation, all these things, how we understand the world visually, we want to give that knowledge, that intelligence to machines. That is computer vision. So typical tasks in computer vision are object recognition, detection, segmentation, depth estimation, so that the robot can navigate easily without colliding the real world objects, right? So this example is object recognition. Given an image, the objective is to find out what is the object present in the image. For example, this is a car in the input image. So prior to deep learning, what was happening is, an expert who has a PhD or some sort of experience in this task would think about the features which are required for the task of object recognition. For example, if you are aware of features like SIFT, SURF, so all these gradient HOG gradient based features were handcrafted. Experts would sit down for years and then come up with a feature which represents the content of the input image into a vector. Feature is basically a numerical encoding of the input. So once you have that feature, now you use a classification technique. Um, like decision trees, neural networks, or any other, your favorite machine learning technique, you can use it on top of the extracted feature to classify. This was the traditional machine learning before the deep neural networks. The deep neural networks do it in a different way. What it does is it removes the expert from this pathway. The feature extraction and classification, both of it will be done automatically from end to end. So we start with random weights. So I hope the previous sessions in this program has covered to some extent feed forward neural networks and back propagation and all that. So I'm kind of assuming. So basically what happens is you start with random weights in the neural network, and then start learning via back propagating the loss and updating the parameters with the gradients, etc. So this feature extraction is not anymore in this deep neural networks. So everything is learned from the data and the objective, right? So this is the big change. We don't need the features to be handcrafted. So the features will be learned automatically based on the task. So this is the big change in the current deep neural networks, current machine learning approach, right? So so features are very, very important to perform any task: object recognition or ASR, automatic speech recognition, or language understanding, anything, whatever the intelligent task we want to solve, the features are very, very important. If you have the powerful features, you can easily achieve all these tasks. That is what is happening in deep neural networks. Let us take again the computer vision application, which is object recognition. Classifying the input image into one of the 1,000 categories: cat, dog, car, clock, all these different daily life objects are the labels. So as I said, these are the features learned at different layers of the neural network. So this is also inspired from how a human brain recognizes the objects. So we know very little things about how human brain works, how it recognizes the objects, how it can see and understand the world. So very minimal is understood. People are working in the neuroscience end to understand more and more about the human brain. But whatever little, how much ever little we know, we get inspired. We means the computer vision scientists would get inspired to build systems that can understand the world, right? So what is understood is basically human brain in the visual cortex. Visual cortex is the part of the brain that is responsible for vision, right? So there people have seen hierarchical processing. So one layer processing the input and forwarding it to the next layer, and it processes the input and forward it to the next layer. So this kind of hierarchy is observed, and the hierarchy in deep neural networks is inspired from there. So we learn features, low-level features like edges. You can see the features learned in these first layer are more like edges and blobs, right? 45 degrees in the positive, 45 in the negative, and all those edges, and then blobs also, circles at top left, circles at bottom left, all these things, right? So on top of it, a combination of these edges and blobs is learned, and on top of it, portions of the objects are learned, and slowly the objects themselves are learned, which are the labels in the 1,000 final layer, right? Each neuron here will represent one class, object class, whether it is cat, dog, car, clock, whatever it is that is there in the data set. So this is a hierarchical representation being learned in a end-to-end fashion. So the experts are not designing these features. End of the training, you will come up with these features, right? This is automatically learned. All right, so this is what is happening in the current AI. So we have a lot of applications. Most of them are driven by deep neural networks. And what is the fundamental? What is the important aspect of deep neural networks? You give data, you design the network, it will automatically learn the useful features and achieve the task. So this is called end-to-end learning, data to task. There is no intermediate step of designing features, right? Feature extraction and the machine learning, which is classification, are automatically happening from the data to the task. That is why it is called end-to-end learning, right? So this is, you can think of the same hierarchy in other tasks like natural language processing or automatic speech recognition, everything. You give the speech, you don't need to really handcraft the features, right? It will be automatically learned, and the classification into the English words. So what I'm speaking, you can have a dictionary It is also a classification. So the number of labels is the number of words in the dictionary. Every time I utter a word, you have to find out which of the dictionary words I uttered. So it's called automatic speech recognition. That is what is happening in Alexa or Siri, all those applications, right? All right. So yes, machines today are getting really intelligent. So for example, you take the classification task, which is object recognition on 1,000 categories. In 2010, this was the error rate. So out of 100 predictions, 27 were wrong in 2010. One system to be stable. Such noises should not affect us. So this is the gravity of the adversarial perturbations. Yeah. So everything seems to be okay, but suddenly, adversarial perturbations spoiled the picture. The stability of the models is highly questioned. Just 1 second. When is the break time? May I know that? Okay, 11:15. Fine. Yeah. So this is, I'm consolidating. I'm trying to summarize the recent research because, I assume the required fundamentals have been covered in the previous sessions. If not, please stop me. Yeah, so that is what I wanted to see. So we also been working in this area because these are very important for the reasons I have explained. It's very important to understand these things and also work on them to make the models robust, right? So in 2017, we also started working on this problem, and we wanted to really dig down. I mean, deep down, we want to understand. So what are the unknown susceptibilities or vulnerabilities of these models? So we started with image specific noise is there. For every image, I can create a noise so that the CNN gets fooled. Later, one more level is you don't need to create every time different noise. Universal noise is there, one noise that can be added to any image so that the classifier gets fooled. But what is the problem here? It requires the training data. A bit of training data is required. As I said, so this is your training data. So the universal adversarial perturbations require some part of this database to be known to the attacker. If you don't have that, if the attacker does not have access to the training data, yeah, it may be difficult to create universal perturbations. That was the state when we took it up. When we started in 2017, that was the state of the affairs. So we wanted to understand, is it really required to have the data? So can we assume that if I don't release my training data, I am safe? So we wanted to investigate that. So that was the belief, although it was not outspoken, but the belief in community, in the computer vision community was, as long as you don't reveal your training data, the universal perturbations are hard to create. But we showed that it is not required to have the data also. We can create noise with only the classifier, right? Classifier means the target CNN, right? The target CNN, if you give that to me, that is good enough for me to create universal perturbation. So this is a realistic assumption because a lot of people, they don't share the data, but they share the classifier, the parameters of the neural network. For example, Google, Microsoft, a lot of people, they train models and they make it public, right? It is not giving the data itself, but the model. It will help a lot because researchers like us take those models and work on our own problems, our own data, our own classification tasks will be there, right? We can take them.
Excuse me, sir.
Yes.
Sorry to interrupt you, sir.
No worries.
Sir, in the forensic department, they can identify that whether the photo is been forgery is done or not, the voice has been any forgery is done. So same kind of knowledge if it's been given to that robo, I think it may filter out the noise and it will still recognize the dog as a dog only, sir.
Right. So that is a good question. So there are remedies how to solve these attacks. I'll cover in the second part. Definitely, I'll discuss about these things. But the thing is, there is no bandwidth actually. For example, these noises can occur real time. Think of a autonomous car driving on the road, right? It has to act within milliseconds. It cannot take more time to analyze and then act. Meanwhile, a lot of stuff can happen, right? Not only that, these things can occur, assuming a robot performing a surgery. These days it is also becoming common, a robot performing surgeries, and it is a video feed. 30 or 40 frames come every second, right? It has to understand within no time. You can understand, right? For every second it has to process 30 images, right? So obviously, if you have that intelligent mechanism developed in that small gap, it may be possible. But as I said, because these systems are time sensitive, we don't have that much time, because forensics is also ongoing research. It requires a lot of sophisticated algorithms to learn, right? If it is off the shelf, yes. But when the things are happening on the fly and the time gap is very small, it may be it may not be a feasible solution, right? I'll come to them. Some of the techniques like blurring, reconstruction, people tried them, but these noises are really strong, sophisticated. You cannot get rid of them that easily. Yes, you may be able to recognize whether these images are doctored or not, whether these images are contaminated. Also, the contamination is very simple. It is only adding of noise, right? It's a very simple transformation. Additive noise is being added. No complex operations are there. So that way it is also very easy to miss. If it is too much doctoring, yes, it is easy to detect. But if it is simple noise adding, it is really difficult. All right, I'll discuss them in detail. Yeah. So what we identified is we don't need to have the training data also. If you give me only the trained model, I can give you the universal noise that can fool the model. So that I'm not going into the detail how we really created that. That itself is a paper in BMVC 2017. So, but I think I want to convey that the models are very susceptible. So whatever you think can make you safe is not going to really make you safe. That is what I want to say. With no access to training data, with only access to the parameters, it is possible to come up with such noises, and not some lesser fooling rate. 80 times fooling, 40 times fooling, it's still dangerous, right? If you say my model is susceptible and 40 times it can give wrong, you cannot sell that model. You cannot really put in real life, real world such models. So it again affects all the deployments. Whatever application you are thinking of, it's not safe to deploy these models. So that is the danger. So just to recollect, we started with one noise per image, and we said it's not required one per image. I can come up with one noise for all the images if you give me some training data. Now one more step is, you don't want the training data also. Give me the model, I'll come up with that noise which can be added to every image or any image. Now the classifier is fooled. So that is the gravity. So what do we understand from all this research? So the basic point is, today's machine learning is intelligent but fragile. So what I mean is, it is easily breakable. It is easy to break. So so such noises, again, it is still wonderful, at the same time shocking to know such noises exist, which can really fool these fool these machines. For example, AI is booming now, right? Think of all those investors, think of all those policymakers that encourage AI. If some newspaper, for example, reports these results, which happened actually, reports these kind of news articles that these guys are not stable, these guys are easy to fool upon adding. So think of reporting such an application where autonomous driving can be really dangerous in the real world. So it can stop them all. It can stop the research altogether in AI. But the thing is, the researchers, the scientists accepted this challenge. We want to make them. We understood that they're not stable. Now we started working, not just now, couple of years. The moment we know the adversaries are there, we started working parallelly how to um, make them stronger, how to make these noises to be impossible, right? So that is the uh, state of the affairs. So one side, researchers are looking for such noises, how to create such noises, because the only way to progress in this area is to create noises first, fool the models first, and then try to understand why it is possible to fool them. So parallelly, you can think of the solutions to avoid them, right? So in conferences like NeurIPS, ICML, International Conference on Machine Learning, there are challenges. So the challenge is to fool the classifier. You can think of whatever way to create such noise. So for the last 5-6 years, it is happening. Adversarial noise challenge, adversarial fooling challenge. So every time they give a data on which you have to fool a classifier. How well you fool, if you are the best in fooling, you will be awarded a big prize actually. So this is all to encourage the research in this area. And simultaneously, there is a defense challenge also. You will be asked to train a model to defend against 10 such attacks. So the best of those 10 in the first competition will be attacking the defense, whatever you submit. Let us say I create a um, intelligent forensic algorithm which will identify the the noise that is being added. So you can attack against, you can defend against the 10 strongest attacks, and how well you are defending, that depends on the best accuracy, of course. And yeah, the bigger prizes are there for that competition also. So these are parallel tracks happening in the research to encourage research in this area and find out solutions that are convincing to both the policymakers and the common man, obviously. Yeah. So right. So this is the state of the affairs. So I want all of you to take a moment to understand the fooling that is happening in this CNNs. So not only CNNs. So although I have explained everything in yeah, so in the CNN context, it can be any generic classifier. It can be an SVM classifier or any other classifier that you like. So every classifier, the same story is there. So of course, before the deep learning wave, also this result was there, but that was considered as a classification problem or the classifier problem. Of course, even now it is classifier problem. Now, because the whole world is going crazy about AI, things are highlighted, a bit exaggerated, I would say, right? But we have to understand that this problem is not new. This problem is there, but because of the new boom for the AI, things are even more exaggerated. Now, every news channel that doesn't even understand these concepts try to report a story, right? Which is bad, because they don't really understand what a model can actually do, what a model can actually not do. They don't really understand. They want to come up with some interesting story to obviously increase the TRPs and all, which is not good for the field, because non-technical people would understand something different instead of understanding the accurate problem, right? So all the people in AI, computer vision, any of machine learning, so we should be very much careful when reporting the such susceptibilities, because they are very important. They can influence a lot of people. That is why. All right. That is all about adversary, not all about adversaries, what they are, how impactful they are, what can they bring into the real world. So the summary is basically it is very dangerous to have such susceptibility, which makes the models very difficult to deploy in all the areas, starting from access granting, defense, autonomous navigation, medical diagnosis, everything. Okay, how are the adversaries generated? We showed that it is possible to create one per image, one per all the images, with the training data, without training data. All that is fine, but actually how they are created. So yeah, so we will cover one method to create such adversaries before we take the break. I think that will be better. All right, so we will see. Consider a linear model. So linear classifier where W transpose X plus B. That is what is happening. So plus B is missing, but your classifier is W and B. W is the weight that operates on X and B is the bias, right? So assume that you're happy learning a simple linear classifier, and W transpose X plus B is the confidence to that class. If it is greater than some threshold, or if it is the highest, you will classify X to be that class, else not. Okay, so this is a simple linear classifier. Obviously, X is the feature vector that you extracted from the input. It can be 512 dimensions or 1024 dimensions. It can be a big information vector which summarizes the content of the input image, right? Now, imagine you're perturbing X by small amounts delta X. Okay, so in place of X, you will have X plus delta X. So I'm adding noise delta X to X, right? So that resulting input is called X star. Okay, so now W transpose X star is equal to X plus delta. So I'm expanding the term. It will become W transpose X plus W transpose delta X. This is the noise that I am adding to X, right? So it will be of the same dimensions as X, right? If X is 512 dimensions, my delta X is also 512 dimensions, because every sample, I may add 0, but it will be there. If I don't contaminate any pixel, the noise added is 0, right? But the dimension is same as the input dimensions. So what do we understand? The activation grows by W transpose delta X. This was the activation on the clean input. This is the added activation because of the noise, right? Let us say it is clear now the activation is increasing or decreasing. It just changes by this much. It can be large because W operates in a high dimensions. High dimensions, again, 512, 1024, it depends. It depends on the problem size. Of course, lot of classifiers do project into high dimensional space for better classification, right? So in high dimensions, if you project through some kernels, even the complex classification boundaries become linear, right? Complex means non-linear surfaces will be approximated as linear in the high dimensions, because that is why classifiers are learned in high dimensions, right? Projecting into high dimensions makes classifications easier, right? So that is the reason people classify in high dimensions. So because of those high dimensions, this quantity is more, right? So I can even approximate, let us say you are uh, changing the component, every component by epsilon. Epsilon may be small because, as I said, after adding, the input should not be very different. It should only, for humans, it should not be different, right? That is how we define adversarial perturbations. It's a mild noise. Visually, it is very, very weak, right? That is why let us represent epsilon as the individual noise added to each of these pixels, right? And average magnitude, every pixel, the noise will be different, right? It need not be the same across all the pixels. Let us say on an average, the magnitude of W is M. W is the vector, W transpose X, this vector. It also be different. See the component of W, let us say 512 dimensions. Again, all these components need not be same, but on an average, you can approximate. This approximation is to understand how bad the delta X can be, right? So that is why let us assume the average magnitude of W is M and the dimension of W is N. N can be 512, 1024, anything like that, right? If you just substitute these things, W transpose delta X is dimension is N, each component is average M, and each component of delta X is epsilon. So the activation grows by N times M times epsilon, right? So it is linear in terms of dimensions. Even an infinitesimal change in the input can cause a large change to the output. I hope you see the point. It's a very simple experiment where we changed x to x plus delta x because of the dimensions, because of the magnitude of w and magnitude of delta x. It can change linearly. If you go, from 10 dimensions to 100 dimensions, the activation grows by 10 times. Similarly, if you go to higher and higher dimensions, because the term is linear in terms of n, the activation grows by large amount. So all the SVMs, most of the SVMs, not all, most of the SVMs are linear classifiers. So based on the linear kernel, if you use, it becomes a linear classifier. And obviously in high dimensions, because of this activation growth, the prior activation, prior meaning before the addition of noise and after the addition of noise will be very different. So this is what adversarial fooling is, right? Before the addition of noise and after the addition of noise, the classifying label is different. The confidences are different. So it is quite possible. So even for a linear classifier itself, it is very clear to see, right? Even a small change, it doesn't matter how small epsilon is, but the n, which is the culprit, right? N makes it linear in terms of n, and the activation grows because of that. All right, so this is not the representative way of fooling. Of course, we will discuss that also. I just wanted to give you, I'll tell you, it is not really surprising that small noises can also make large changes, because the dimension, in this case, it is clearly the dimension that is making the problem worse. Because of the dimension, small noises added to the input will cause large changes in the output. If you see, in when we study signals and systems, we study about the stability concept, right? When do we say a system is stable? It has to provide a bounded output for bounded input. But here, if you see, for bounded input, the system is causing unbounded or not so bounded output. So that way, this noise makes the CNNs or any other classifier unstable, right? So you can think of this system as unstable system, because small noises or small changes in the input are causing bigger changes in the output. So that is how people see in the information front. These CNNs are the classification models in general, not only CNNs. So this is how the linear model, in case of linear models, it is understood, right? So nonlinear models. So if I start this module, it is a little complex. So probably it is a good time to take a break, but it is only 10:45. Okay. See. Yeah, it is a continuous module. Okay, let me continue anyway. Okay, so linear models, we use linear models, but they have limitation of learning simpler classification boundaries, right? Not every problem is linearly separable. Not every classification is linearly separable. There will be complex classification surfaces that requires to learn sophisticated models. For example, neural networks are one kind of sophisticated classifier where they can learn nonlinear classification boundaries also, right? So, the concept that we're going to discuss now require backpropagation and gradient computation. Anyway, I'll cover briefly, but stop me if it is really not clear. Okay, feel free to do that. So how do we learn neural networks? There is a architecture which connects the input layers to hidden layers and then output layer. And then there is an objective. Objective means loss function. Loss function gives you how good or how bad the predictions are compared to the ground truth. it will compare the ground truth and prediction. And if they are far away, the loss is more. If they are very close, the loss is small. So the objective in training is to reduce the loss starting from very high value, because if you start with random parameters, the loss will be very high, and you compute the loss and back propagate the gradients and update the parameters. Slowly it reduces. It is called empirical risk minimization, right? Risk or loss or objective, everything is same. The mean, all of them mean same, right? So in this process, gradient descent is the algorithm generally we use for computing. J is the loss function, theta is the parameters of the neural network, X is the input, and Y is the corresponding label. X can be the input and Y can be the label, right? So basically we compute how good the parameters are, right? And then you compute the gradient of the loss with respect to the theta. Theta is the parameters. Why do we do that? So the objective is simple. Gradient descent, what it does is, gradient of any function by definition gives the direction in which the function increases, right? But we want to reduce the loss. Loss is mismatch between the prediction and the ground truth. We want the mismatch to be reduced. We want the prediction to be close to the ground truth, right? That is why we want the loss to be minimized. But we know the direction of increasing the direction, the increase of the function. So in order to decrease, we take the opposite of that direction. So with the negative sign, we take the gradient. So if this direction increases, obviously this opposite direction should decrease the function, right? So we move the parameters in the opposite direction of the gradient. That is called gradient descent, right? So this parameter update. So now theta t becomes theta t minus 1 plus this quantity. Eta is the learning rate. How far you want to move in this direction. You can move far, you can move only slight bit. So eta is the learning rate, the step you take in that direction. So this is what the general gradient descent is, how we come up with the loss function, and then we compute on a mini batch. Mini batch is a subset of training data you take and compute the loss and compute the gradient of the loss with respect to every parameter and update the parameter one step, right? So this is gradient descent. So I just want to know, can somebody please let me know, is this covered in the previous modules? Ravi Garu?
No, sir. Not.
Sorry?
It's not covered, sir.
Okay. So do you want me to spend some more time on this? This is a little bit important.
Yes, sir.
Okay. Okay, let me just see if I have the diagram. Yeah. So this is how you can think of gradient or loss function. So loss is basically, so neural networks are layers of neurons connecting from input to the output. Input can be an image like this. Output can be a label. Label means 0, 1, 2, and so on. Capital K minus 1, where capital K is the number of labels, right? In the ImageNet problem, it can be 1000. In the MNIST kind of character or digit recognition, it can be 10, 0, 1, 2, and so on, 9, right? That is the label. So when you start the training, you don't have the suitable parameters to correctly identify the input. You will be making some mistake. So initial parameters definitely make a big mistake. How do we find our predictions, how good they are, how bad they are? So that is where the loss function comes. Loss generally gives the amount of mismatch between our prediction and the ground truth. Ground truth means the correct prediction, right? So ground truth for this input is dog, right? Initially, if I start training, network may not predict a dog for this input. It may predict car, because it depends on the parameters. It's randomly initialized parameters. So a mismatch between prediction and the ground truth is computed using the loss function. Ideally, we want zero loss. That means we want every prediction to be same as the ground truth. It will not happen, but we will bring that close to zero. If you see, this is one such location which is very close to 0. 0 is this level. So here also, this is another local minima where the loss function is very close to 0. So ideally, we want to operate here so that the loss is very minimal, right? So loss again depends on the task. So it can be simple y minus y hat whole squared, which is a mean squared error loss, or it can be a cross entropy loss where you want to compute the distance between two probability vectors, right? So one probability vector is ground truth, one more probability vector is the predicted. So distance between two probability mass functions is computed using cross entropy loss. It is coming from the information theory where you minimize the distance between these PDFs or PMFs, because this is discrete probability mass functions. So again, the task decides what kind of loss to be used. It depends upon the task, which is the labels basically. All right. So once you start with the random parameters theta, as I showed here, so theta is the parameters of the network, and x is the input, y is the output. So if you apply theta on x, you will get y hat. Y hat is the predicted label. And ideally, we want that to be close to y. It may not happen. So you compute the distance between y hat and y. That is the objective of the loss function, right? So as I said, it can be a simple mean square distance between y hat and y, or it can be a cross entropy loss. Cross entropy loss is distance between probability mass functions, which is the commonly used loss for classification task. Okay, so once you have that loss computed, you can take the derivative with respect to theta. Yeah, so the objective here is, again, it's a search problem. We are searching for that parameter theta. So the x-axis in this diagram is theta. We don't know where we need to stop, which theta is ideal. We know that we need to pick that theta where the loss function is minimum. So j of x is the y-axis, x is the, sorry, it can be input or theta also. So we need to find out that location where the loss is minimal, right? So that is where the gradient descent is coming. Gradient descent basically is an opposite form of, okay, let me restate it. Gradient by definition gives the direction in which the function increases, but we want the loss to be minimal. So from the random initialization, we come back, let us say, sorry, my bad, okay. Let us say your random initialization is somewhere here. If you compute the gradient, it will give this direction in which the function is increasing, right? So if you go horizontally towards right, the function is increasing, right? But we want to go down because the function should be minimal. So you slowly come down and reach this point, and upon here, there is no minimal, right, than what we have. So it is not decreasing further. So you will stop here. So the objective of training is to reach such a local minima. Okay, so that is what is happening in training. So this is what a single equation guides the whole training. Whatever application, it can be Siri, it can be object recognition, CNN that is employed in autonomous cars, Alexa, anything. All these neural networks are trained using this gradient backpropagation and gradient descent. All right, so this is completely unrelated. There is slight concept from this discussion that we are going to use, right? So gradient is very important. So if anybody of you is interested in doing machine learning using deep neural networks, you need to understand gradient. Gradient is very powerful concept. So gradient, as I said, gives the direction in which the function increases. So if you compute the gradient of j with respect to some parameter, it can be theta, it can be x. So what it means is, it gives the direction in which the function increases. By definition, that is the gradient, right? So if it is with respect to parameter, the gradient is really helpful in learning best parameters to reach that, low point where the loss is minimal, right? If it is fooling the models, if you want to create an attack, that in that case also gradient is the key. Gradient is the tool that is used for fooling. How? Let us see. So now I'm computing the gradient with respect to x. That means I am operating in the input space, not in the parameter space, input space. So input space can be highly, huge dimensional. For example, if I take a image, which is small image, 28 pixels by 28 pixels, right? 784 dimensions it will have. 784 dimensions, it is even difficult to imagine, right? So we are operating in that dimensions, 784 dimensions. That image is a very small image. For example, what is the dimension of the images that we take in our smartphone? It will be in megapixels. The dimension will be in megapixels, right? So 1600 by 1800 is it's not a big size for us, right? Imagine, so if at all you are operating in such big images, you are operating essentially in very high dimensions. So basically what is happening is you are moving from one point to another point in those dimensions. So here x is the input, y is the corresponding label, theta is the parameters of the model. Let us say the model is already trained. Somebody has given you the trained model, which is performing very good. It can recognize with 85% accuracy.
Excuse me, sir.
Sure.
So what is parameters, sir?
So parameters is the weights connecting the layers in the neural network. So how does a neural network look like? Neural network looks like, let me just go back to the initial slide. That's a good question, sorry. Yeah. So here, if you see, this is input. It can be three-dimensional vector, and this is another hidden layer. Between them, there will be connections, right? This is X, and there will be a W to operate on that X to get the output here. So that is the neural network construction. How the neural network is constructed is layer by layer data propagates in forward direction, right? So parameters are weights, both are same. Weights are sometimes referred to as parameters. So they are represented using theta. So in this example, what I am showing, input is three-dimensional. All the hidden layers are also three-dimensional. So the weights connecting this neuron will be 3 cross 1. W1 will be 3 cross 1. W2 also, because it is connecting to all the three input, it will be also 3 cross 1. One second. Sorry. So those are called parameters or weights of the neural network because they connect different layers. So this is how information is feed forwarded in the neural network. So from the input, it enters the neural network, and then one transformation by another transformation, the data gets processed. Towards the end, it will be a label predicted. So there are only three labels. This is the output layer. There are only three labels. It can be car, dog, and cat. I'm just giving an example. Or it can be a binary classification, whether it is a car or not a car. In that case, there will be only one neuron, one connection. Why? Because it can give the probability for car, right? If the probability is greater than 0.5, you can say it is a car. If it is less than 0.5, you can say it is not a car. That is called a binary classification because there are only two labels, right? So parameters are the weights connecting these layers, right? Sorry again. Yeah. So neural networks. So I kind of assumed that the feed-forward neural networks module will come up with these things. That is why I kept the presentation a little higher level. But if that is the case, I may take maybe. So I just want to know whether it is required for covering the feed-forward neural networks in a bit more detail, because that way you will understand the contents better. If it is required, I can adjust 10-15 minutes. I have the slides also, probably I can bring in and we can discuss that before we go further. Is it okay?
Yes, sir.
Yeah, just give me a second. Did somebody say something? Sorry. You can see the screen, right? I'm still sharing.
Yes, sir, it is visible.
Okay, great. So let us try to understand what neural networks are, or how they learn the task at hand. Okay, so these are some previous slides we had in our lab from IISc. So some of my colleagues, Suraj, I think, has prepared them. We use them commonly, so no problem. Right. So generally, this is what neural networks is. A simple neuron. Let us try to understand first. So neural network is a combination of neurons. Neuron is inspired from, again, from the human brain or animal brain, where the cells of brain are called neurons. They'll have, yeah, I don't remember the names exactly, dendrites, axon, to collect the input and then perform some neuroactivity and pass on the information as electrical pulses. Right? That is that is the inspiration for artificial neuron also. For example, this is the input x1, x2, and so on xd. It's a d-dimensional vector. Now, the neuron has to operate on this input. How? It will operate with weights W1 and so on WD. W1 multiplies X1, W2 multiplies X2, and so on WD multiplies XD. And the summation of all these multiplications is taken, and there will be a bias again added on top of this summation. You see this sigma I WI plus B. This is a typical neuron operation. So x1 to x2 is the input on which the neuron is operating. It operates through weights or parameters. The W is the parameter, W1, W2, and so on WD. It will take a weighted summation, and the bias is also added. So this is inspired from the human brain or animal brain in general. So they wanted to see how the brain is taking the input. Input comes from nose, eyes, and other sensory organs, right? Whatever input is taken and which is presented as an electrical pulse, x1 to xd, will be taken through these weights, and then a bias is added, and there is a nonlinear function g also applied. Nonlinear function can be threshold. Simply, if this input is threshold, if this output computed is greater than 0.5, you output 1. If it is greater than or less than 0.5, you output 0. So different types of nonlinearities are investigated in literature. So generally, the nonlinearity helps in learning complex functions. So this is a simple neuron. So as I said, nonlinearities can be sigmoid function, tan H function. A simple threshold also can be a nonlinearity. So this is a basic neuron. It operates on input vector with weights via weighted summation, and there is a bias, right? So once you have this kind of a neuron, so neural network is basically putting them into a network structure. For example, let us take this simple example. Again, the input is x1 to xd, d-dimensional. It can be my speech. It can be an image vectorized. For example, 28 cross 28 image. You can make it a matrix. You can make it into a vector. It becomes 784, I think, I'm not sure, 784 or 764 dimensions. So you can imagine x1 to xd as that input, right? Now I have, let us say, 10 neurons in this first layer. So this is neuron 1, neuron 2, and so on, neuron 10. Okay. So each of them will have a corresponding set of weights. Everyone takes the weighted combination, but weights are different. W1 to WD for this neuron are different. W1 to WD for this neuron are different, and so on. Because each of them will learn different features. It will try to recognize text in the image. It will try to recognize animals in the image. Maybe I'm just giving you examples of features, right? They may learn different things. For example, even in human brain also, there are specific regions that respond to specific smells, right? So there will be specific regions in the brain that responds, that will fire for specific stimuli, right? So different visual stimuli will be recognized in different parts of the brain. Similarly, different concepts in the input will be fired or recognized by different neurons. So this is how the information is processed. They apply the weights on this input and compute the activation. So the output of neuron is called activation, because general understanding is that neuron fired or not fired. If it fired, what it means is the concept it is designed to find is present in the input. For example, it is looking for dogs. If there is a dog in the input, it will fire saying, I found dog. If dog is not there, it will not fire. The activation will be very low because it was looking for dog and dog wasn't there. Similarly, let us say this, so who assigns what to learn? It will come automatically. So we cannot assign that normally. We will understand once the training is over. Okay. So there can be edges, there can be blobs, everything. Every neuron will learn some concept. Generally, there may be some neurons which are underutilized, which may not learn anything. But general understanding is they are required for learning different patterns, different input stimuli. All right. So this is how a neuron will interact on the input. And if you have a row of neurons, it will be called a layer. And if you have another such thing, it will have multiple layers. And finally, you will need output also, right? So it can be a binary classification. For example, you are looking for car or not car classification, right? So this neuron, which is output neuron, f of x. F of x is basically, the classification output. If it is 1, that means there is a car. If it is 0, that means there is no car in the input image, right? So again, this neuron is also pretty similar. It will have weights operating on this layer, not on the input, because this is only operating on top of the first layer. It will have a bias for the same activation, right? So this is how neural network are created. The weights are called parameters. It will be represented either with W or with theta, right? So initially the weights are initially randomly initialized, and then you have to go on uh, updating them. Updating happens through back propagation. So back propagation, I'll try to quickly cover. Um, Please. Yeah. Oh, okay. It's 10, 12. Okay. Yeah. So, all right, I'll stop here. So I can probably, take 5-10 minutes after the break to quickly cover back propagation, how the neural networks are trained. It is very important because, um, so obviously I would like you to also try training neural networks on some of the problems at the end of the day. And obviously the adversarial perturbations, once you understand these concepts, that will be a little easier to understand. Okay. So yeah, so back propagation is a detailed concept. Let us probably wait for the break. Okay, yeah, we can break now. Immediately after the break, I'll cover this one. Okay. Yeah. Yes, yes, I am ready. All right. So let me quickly recap. So we are taking a small detour basically to understand how the neural networks look like, what is the structure, how they propagate the data, and how they learn the weights or parameters to do the task effectively. Right. So this is how a very simple neural network looks like. The orange layer is the input layer. Sorry for the noise. Just hold on for a second. Yeah, I'm really sorry about that. There is some vehicle going on there. Okay. So this is the hidden layer, one hidden layer, and there is a output layer with only one neuron. This is the output neuron shown in green, right? So this is the input matrix where every row is one input, 3 comma 5.
Sorry, sir.
Sorry.
Sir, we cannot see your
Oh, is
screen,
it? Okay,
sir.
okay. Is it visible now?
Yes, yes, sir.
Yeah, yes, sir.
Yeah, my bad. I'm really sorry. So we were looking at the architecture of neural network, how the forward operation, how the backward operation happens. So let us say this is a simple neural network trained to recognize cars in the input image, or let us say some sort of a detection of objects. Okay, so this is the first column is the input layer, and the next column is the hidden layer, because this is hidden from the input and the output. There can be multiple hidden layers, but this is a simple example with one hidden layer where 3 neurons are there in this layer. This is the output layer. There is only one neuron shown in green, right? As we discussed earlier, neuron is same W. There will be a weight matrix which which connects to the previous output or input directly, right? So input is two-dimensional. Each row, this is the input matrix. There are 3 rows. Each row is one input instance. 3 comma 5 is one instance, 5 comma 1 is another instance, 10 comma 2 is another instance. Okay, 3 will be operated on here. Is column wise we have to operate. Basically, I just mapped it to make it easier to understand. Okay, so this will be operating based on the weights. So this is the input. You apply input here. 3 goes here, 5 goes here, and this is the layer which takes the input. So every input is connected to this, every neuron essentially. So as I showed, one weight connecting to 3, one weight connecting to 5, right? So 3 times first weight plus 5 times the second weight. Here also 3 times the weight connecting, 5 times the weight connecting. Here also 3 and 5 are there. There are 2 weights connecting. 3 times this weight, 5 times this weight will be here. So for simplicity, I'm omitting the bias, plus B1 here, plus B2 here, plus B3 here. You have to imagine. So it will be too much to put. That's why I just simplified. But imagine there is a B also operating. Okay. So once you have this thing, this is how the first layer will be computed. And similarly, next, the output neuron will also have its own weights, Ws, which operate on the output of these neurons, right? So output of these neurons, after this multiplication and bias addition, there will be a nonlinearity function also. It can be a sigmoid function, it can be a threshold function, it can be tan H function, anything. You can apply the tan H function on these computation, okay? So I'll show you. This is how it looks. Okay, so there will be X input and W is the weights connecting. W transpose X will be applied and there will be a bias also applied. And if there is a nonlinearity, yes, it will be there. The nonlinearity will be applied. So that completes one layer of operation. Okay, this is all for forwarding operation because input to output is forward, right? Yeah, so these are typically the operations. As I said, after this W transpose X plus B, there will be a nonlinearity also. It can be ReLU. As I said, there are different nonlinearities. You can take a look at them. They simply do some operation basically. All right. So yeah. So you have to imagine weights here also on the output of these hidden layer of neurons, these weights will operate. W11 superscript 2 times A2. Similarly, W21 superscript 2 of, here it is B2 or whatever you assign. Similarly, this also operates. And one quantity will be computed at the output. So typically, we expect that to be probability for the presence of car, right? If it is greater than 5, it means greater than 0.5, it means there is a car. If there is the probability less than 0.5, that means there is no car. So it's a simple binary classification problem, right? So this is how the feed forward neural networks work from the input layer to the output layer. So whatever the output that is computed by the output neuron is called y hat, right? Y is the actual output. Y hat is the predicted output, what the network is predicting the output to be, right? Ideally, we want y hat to be closer to y. Y is the actual output, right? So in case the input is car, output is 1, right? With 1 probability, there is car. We want y hat to be close to 1. Ideally, we want 1, but typically you see 0.7, 0.8, close to 1, towards one side you see, right? So that is how you compute the prediction. Once you have the prediction, the next thing is to compute how good the prediction is, how accurate the prediction is. For example, as I said, y is shown in green and y hat is shown in blue. So the mismatch between the y and y hat is called error. So this is the error in prediction. We want to make this error to be 0, right? We want the y hat to be equal to y. Then we say our neural network performs the best because 0 error, it performs as we want it to perform. So this is called error in prediction. The objective of training is to minimize this error. So we have to come up with a loss function. So one simple loss function can be e squared, y minus y hat, the difference between predicted and the ground truth. It can be called E, which is y minus y hat, and the summation of all those things, because there will be number of training data, right? You can have 1,000 training data, 10,000 training data. You can compute that error in all the training data and try to minimize that loss. So this function, which computes the mismatch between the predicted and the ground truth, is called loss or cost. It can be represented with J or L. Typically, J or L is used to represent the loss function. All right. So this is the feed forward operation. Starting from
Half is there. 1 by 2 is square. Why this 1 by 2 is there?
Yeah, that is a computational simplicity. If I take derivative, it will be 2e, right? That 2.5 will be gone.
Okay.
Yeah. So it has no other meaning than a computational facility. If you just differentiate with respect to e, 2e, 2.5 will be cancelled. Yeah, whenever there is a square, because it will be differentiated and made equal to 0, that 2 gets cancelled with half. So that is a reason for half. There is no more reason. Yeah. So this is how typically a loss function is designed. And training is to minimize this loss, right? What is training? How do we say, or when do we say the network is trained? When it performs with minimal error. We say because of the training it received, it is performing with minimal error, right? Training means minimizing the error, which is learning the task, learning to recognize the cars, learning to recognize whatever task it is, the handwritten digits, or learning to recognize what I spoke. All these things will be learned via minimizing the loss, right? So that is where the back propagation comes. This is where the feed forwarding ends. Feed forwarding starts with the image or input and passing on the input to different layers all the way to output and computing the error. So once the error is computed, then we say the feed forwarding is done. So backward propagation, when is required? It is required only during the training. Backward propagation means training. What it does, how it does, we will see. Right. So this is all discussed. Yeah, this is also fine. Right. So this is the loss. J is the loss. How do we compute? We take the summation on all the training data, summation is y minus y hat. This is just y hat, how the y hat is predicted, right? You take the x, apply the first layer, and apply the nonlinearity. On top of it, apply the second layer and apply the nonlinearity. That becomes y hat, right? So if you if you remember the minimum maxima from +2 level mathematics, we will compute the objective function and take the differentiation and make it equal to 0, saying that at maxima or minima the derivative will be 0, right? So if you remember the the graph that I showed, where, let me show it again. So at minima the gradient will be 0. So we are trying to find this minima where the gradient is 0. Sorry. Right? So because it is a non-convex problem, it is not very easy to find that. So dou J by dou W. W involves every parameter. There are 1, 2, 3 times 2, 6, and then there is 3, 9 parameters here, right? So each neuron will have 2. So 3 into 2, 6. And here, each neuron will have 3. There is only one neuron. 6 weights are there, right? So counting the number of weights is also very important, because it will give the complexity of the network. If the network has more weights, that means it has more capacity, more sophisticated the network is, right? So you will have this partial derivative with respect to each of these weights, dou J by dou W1, W2, W3, and so on, W4, W5, W6, W9. So that is required to update the weights. You start with random weights, and you want such a weight where dou J by dou W will be minimum, right? So that is the objective of back propagation. Once you compute the loss, you compute the gradient, right? So there are, yeah, so this is the meaning of gradient, right? So dou J by dou W is positive. That means it is increasing in the direction. So how J varies if I change W? If I increase W, the J also increases. That means it is in the increasing direction. If I increase W, if J decreases, it is in the decreasing trend. The J with respect to W is in decreasing trend, right? This is how we generally understand the sensitivity and the meaning of gradient. So in one dimensions, it is like this, right? So the same fundamental you apply to more dimensions, because your W's are more, 9 in this example. So you have to apply one by one, basically. All right. So whatever I have discussed, yeah. So you start with, so this is the 3 dimensions. Let us say you have only 3 weights, W1, W2, and W3. So it is very small problem. In practice, we will have millions of dimensions, right? VGG, AlexNet, ResNet will have lakhs of parameters. So you are in a very huge dimensional space. But for understanding, let us try to imagine only 3 dimensions, W1, W2, and W3. So here, the initial weight or loss is here. So ground is 0. So when you have the value on this plane is 0, right? So initially you have a loss which is higher, and slowly you try to reduce it. How? You try to compute the gradient and move in the negative direction. So this is how you move to this point, and again this point, this point, this point, and slowly you reach a minimal point. That is when you stop your training. Okay, so this is the winner where dou J by dou W is equal to 0. In this problem it is, but it may not be 0 all the time. Whatever minimal you can find, you find and stop there, right? Yeah, so once you reach this, you say the training is over. So generally we want the global minima where this is the minimal, the least possible loss value. But sometimes it may be difficult to find, so you need to be happy with a local minima. Local minima means it is a small point within the local neighborhood, it will be minimum. But if you go beyond, there will be another minimum smaller than this minimum value. So because the optimization itself is a very active research area, so people are looking at finding ways to reach these global minimas, not to get stuck in these local minimas. All right. So that is how generally you perform the backpropagation. Once you compute the loss value, take the gradient of loss with respect to each parameter and update that parameter W by adding the negative of the gradient. So that is the fundamental. I hope I have conveyed the meaning. So because the reason is also simple, gradient generally gives the direction in which loss increases. But we want the loss to decrease, right? Y hat and Y has to be close. So we need to decrease the gradient. So what to do? You go in the opposite direction of the gradient. So you increase or decrease the parameter going in that direction. So that way, if you go step by step, your loss value will be minimal. Okay, so this is how neural networks get trained. It's a very old algorithm designed in 1960s or so. Even in 2021, this is the same algorithm used by everybody who trains the neural networks. Somehow, this is a very strong and very important algorithm in deep learning. So yeah, so I urge you to take some more time. Of course, I covered it in a very fast time. The fundamentals I tried to cover. What is the funda? How the feed forwarding happens? What is the fundamental of going backward? So what is the meaning of going backward? Going backward means compute the gradient and move in the negative direction of the gradient because we want to reduce the function. The function here is the loss. Okay, so that is how we go about training the neural networks. All right, so this is what we wanted to understand adversarial perturbations. So let us get back. So before we get back, if you have any questions about the training, feed forward and backward propagation, please try to bring it up now. Feel free to do that. I'll try to explain it a little more. Otherwise, we can go to the adversarial stuff. All right, so where were we? We tried to understand linear models. In case of linear models, changing input by small amounts creates large changes in the output. So we understood that. Why it happens? Because the dimensionality is a major point. Because of the dimensionality, the change in the output is very significant. It may cause the labels also to be changed in the classification problem. That is fine. How about nonlinear models? So nonlinear models, what happens is, so this is what the gradient we use in training, gradient of loss with respect to the parameters. But what about the gradient of the loss with respect to input x? See the difference. The gradient here is with respect to the weights or the parameters, right? The W's. But here, the weight is with respect to input. So the gradient is computed in the input space. Again, the meaning is same. Gradient means the direction in which loss increases. So we are moving in the input direction for increasing the loss. Increasing the loss means y hat and y will be far away. That is fooling, right? In case of dog, if you predict cat, it is going further from being dog, right? For example, the ground truth label is dog and you are saying paintbrush, the loss is increasing, right? So fooling means increasing the loss, increasing the mismatch between the ground truth and the predicted value. So now applying this principle, people change the input. How? You take the direction of the gradient and then move in that direction a little bit. So let me show how it looks like. For example, this is the input. So again, so you need to imagine things in a very high dimensions. It is a 256 cross 256 image, right? You will be in 256 squared into 3 times dimensions. It is a very huge dimension, right? But the diagram we have is a very simple diagram here. It's a one-dimensional space. So the x-axis is the input, x, right? If you move in the input direction, the loss also will change, right? Here it is minimal and slightly it is increasing. And here at this point in input, the loss is very minimal. Probably you are here because after the training, the loss will be very minimal, right? So now what you are trying to do is in the input space, you are trying to compute the gradient dou j by dou x, and you are moving in that direction slightly. Again, we are not going in the opposite direction. Here, you are going in the direction of gradient. You are increasing intentionally the cost value. The loss J value is being increased. That means the mismatch between the ground truth and predicted will be increased. It is a soap dispenser, right? This is an image of soap dispenser where this is one of the 1,000 categories in ILSVRC. So I have a trained model. So I computed the gradient dou J by dou X. This is how it looks like, the direction. Now I add this to the input. So X0 star will be gradient added to the input. So now if you compute the losses, so loss for soap dispenser will be 0.76, and which is very minimal. I'm not showing the other 999 losses. Sorry. Yeah. So because the loss for soap dispenser is minimal, the predicted label is soap dispenser with confidence 54.6. But the moment I add this, it will increase the loss to 1.18. Previously it was 0.76, and now the loss is 1.18, right? The loss for ostrich class is now minimal. That is why the predicted label is now ostrich, not the soap dispenser anymore, right? So it is a intricate process. Try to understand what is happening, because you computed the gradient in the input space and you are moving in that direction, which increases the loss for the ground truth, right? Ground truth is soap dispenser. You computed the loss and you took the gradient and moved in the direction. Because of that, the loss is increasing from 0.76 to 1.18. While this is happening, loss for other category, which is ostrich, is decreasing. Because of that, the confidence for that class is increasing beyond the soap dispenser category. That is why, because the confidence for ostrich is more now, the CNN will predict this label as ostrich, but we know it is soap dispenser, it is not ostrich. So this is how fooling is realized in nonlinear models, right? The gradient with respect to input is the key here. So yeah, the only difference is, you have to remember, while training, the gradient is computed with respect to weights, and we go in the negative of the direction, because the objective here is to reduce the loss. But here, gradient is computed with respect to input, and we go in the direction, because this is fooling. We want the model to be fooled. We want the model to misclassify. So intentionally we go and increase the cost or loss. So you can clearly see 0.76 becomes 1.18, and because of that, the confidence of the ground truth, the true class, decreases from 54.6 to 4.6, 50% reduced, right? Because of that, some other class will get a better confidence and the label will be predicted as ostrich. So this is how fooling is realized in the nonlinear models, right? So this is only one way to realize fooling. There are a lot of other ways people are investigating to find out different ways to confuse the model. Why? Because to understand whatever in how many ways the models can be fooled. Although they are intelligent, they are easy to be fooled also. So all these approaches are called attacks, because attack means creating a noise with which you can confuse the model or you can fool the model. So these are called attacks, similar to other cryptography or other computer security areas where people try to attack by doing something, right? So denial of service or creating viruses, all these called attacks in computer science. This also is new attack in computer science, which is creating noise. When we add to the clean sample, the intelligent machine that is classifying correctly will now be fooled, will now misclassify with high confidence again. So this is one way in which the noises, adversarial perturbations, can be created in neural networks. All right, so this is how some more examples I want to show. So the noise looks like this, and upon adding, it will not be very strong. For humans, we can still look at the image and find out what the object is, but the machines get fooled. Right. So if you want to really understand, I can give you the mathematical equations also. So you can compute the gradient with respect to x, and you can take the sign and then multiply with epsilon. Sign means whether it is positive, 0, or negative. Each component, it is a vector of input dimensions. Input is 256, 256, 3 in the example. So it will be of that many dimensions. And if you take sine of it and multiply with epsilon, so you will have more control, right? Instead, if you don't have this thing, each of these components will be different, right? So the perturbation has to be uniform. You have to, you can't add as much as you want. You can only add small perturbation, which is limited by epsilon, right? Each of these pixels cannot be modified by more than epsilon. So this is how you can realize x is the original image. You computed the gradient of j with respect to x. That is how we represent dou j with respect to x. So j also, it takes input as x and y true. True means the ground truth class. Y true means is the label of the ground truth. Okay, so once you have this gradient, because there is a limitation on how much you can add to each pixels, what you do is you take the sign and multiply with epsilon. So that way you have control on the noise that is being added. So this is a very famous attack called fast gradient sign method, which is invented by Ian Goodfellow in 2015, around that time. So this is kind of the first work that that made every deep learning scientist shocked, because until then things looked very comfortable. Things looked, very promising, because the errors were coming down every year, and people started using deep learning for every task, not only in computer vision, speech, language, not only in computer science. People started using deep learning in astrophysics and biology, medicine. Everywhere AI deep learning has been used, and suddenly things turned out to be like this. Stability issues, fooling issues started to show up, and then more and more people started to look around, look about these attacks. So now there is, in every major machine learning conference, there is a separate track for adversarial perturbations and challenges to create attacks and defend them also. Defend them means you will be attacked with such noises, and you have to be predicting correctly. You have to avoid getting fooled. So that is also, as I said in the first session, these are very hot areas in machine learning and deep learning now. All right. So just to warn you, this is the simplest of the attacks, first of its kind. There are later a lot of such attacks created. Okay, so just to wind up the gradient concept, because gradient is very, very powerful. I want you to see how easy to fool such noises, such machines. So let me
excuse me, sir.
Sure.
So in the gradient with respect to input, there we are supposed to, I think, tune only weights. Why we are tuning the inputs, sir?
Correct. So in training, we have to tune the weights. When we are training the neural network, what you said is correct. We have to tune the weights. But here, my intention is not to train the model. My intention is to fool the model by creating a noise in the input space, right? So because I want to create a noise, which when I add to input X will increase the cost for the ground truth label. So increasing the cost for ground truth label means increasing the mismatch between the predicted and the ground truth, right? So this is what fooling is. If you increase the predicted difference between predicted and the ground truth, that is what fooling is, right? So
yes, sir.
Yeah, my intention here is to fool the machine. That is why I'm creating the gradient with respect to input. The model is already trained. So now there is no concept of training the model. The model is trained and given to you. Now I am attacking the model. Attacking model means by adding the noise, the model should fool. the model should misclassify. So that is attacking part. So this second part is all about attacking the models. Yeah, what you said is correct. In the normal training, we compute the gradient with respect to parameters, dou j by dou theta. So this is the normal gradient. So now when we want to fool, we take the trained model. Already all the training is over, the minimized loss is achieved, and the model is given to you. Now I compute then the gradient with respect to x and go on adding the noise like this. Now if you use this x adversarial, x is the clean image, x adversarial is the noise added image. So these are all x adversarial, these are x. This is the noise created, which is based on the gradient. I hope I cleared that out, right?
Yes, sir.
Okay. Yeah. So just to understand visually how the gradient in one dimensions look like. So this is, let us say this is the loss. On the y-axis you are plotting loss. On the x-axis you are plotting the input. One-dimensional input, simple one-dimensional input. So from here, as you increase the input, the loss is coming down, decreasing until here it decreases. And then if you still increase the input x, the loss is increasing and reaches maximal here. And again start to decrease rapidly, it will decrease. This is where it attains the minimum. And again, it is increasing. So let us say this is the behavior. And I am starting from here. My x is here. X is this input, clean input. So I am here. I'm getting relatively less loss only. Now what I'll do, I'll compute the gradient. How do I compute gradient? Dou j by dou x. So as I said, gradient gives the direction in which function increases. So this is the gradient. In this direction, the function is increasing, right? So I'll add that much. So in that direction, I take small step. So if I go now, the loss is increased now because the y-axis can be, earlier it was 8. Let us say, I'm just giving some numbers. Earlier it was 8, now it will be 10. The loss is increased, right? From here, we move to here. So this part is x star. Here x was there, now we moved a little towards left on the x-axis. So that is how we create x star. Now clearly loss at x star is increased because loss means the mismatch between the predicted and the ground truth. We realize fooling. That is how we realize fooling. So meanwhile, the loss for some other category will be lesser than this loss. Immediately the network predicts that label. For example, for paintbrush, the loss can be less than 10, right? So that is how the network prefers to predict paintbrush instead of dot. So this is a little sophisticated concept, but try to imagine moving in high dimensions, and if you move slightly also, the loss is increasing drastically, so that some other labels loss will be smaller, and then the network prefers to that label, which is realization of fooling or misclassification. Yeah, this is a very simple example, only shown in one dimensions. Okay, so just try to interpolate this in the high dimensions. All right, so this is only FGSM, fast gradient sign method, the first of its kind, the simplest of its kind. All that it requires is computing gradient. You just compute the gradient, take small step, epsilon step in that direction, add it. Immediately you have adversarial image. So simple. All that you need to do is one back propagation, computing the gradient with respect to input. Very easy, and very effective also. It fools quite a number of times. All right. So are there other ways to generate adversaries? Yes, there are hundreds of ways. So thanks to the research in the past 5 years, there are hundreds of newer methods to generate such noises easily, fast, and very strong. So a lot of such attacks are there. So I might be wrong. There may be hundreds and thousands of attacks also now. Yeah.
Excuse me, sir. So this adversaries we create through same neural networks only will generate, sir.
Yes. We whatever model you trained, you can use the same network to create that adversary. But if you remember, there is another property called transferability. Because of the transferability, you can take that network to unknown model, and still it will perform fooling to great extent. So let us say this is the model. The green model is what you have trained in your laboratory using your own data. You created, and then you can take this adversarial sample to another network, which is blue network. You don't know what that network is, how many layers are there, what data it is trained on. But you simply know it is also a classifier, and then you can apply and fool that network also. So this is also experienced. You don't need to have the same model. Okay, you can have your own model and you can still attack other models. So this is called transferability, because you are transferring the attack from green model to blue model. Okay, so is this your question, right?
Sir, I would say in other ways, just for my clarification, sir. Suppose if I change, if I update my weights, it will work as a good network. If I update my input, it will work as a adversary network. Is it true, sir?
That is correct. You understood it correctly. If I change the model's parameter to reduce the loss, it is doing good to the model. If I change my input to increase the loss, it is called fooling. Suddenly, this small difference makes the fooling, makes the attack.
Thank you, sir.
Yeah, no problem. Yeah, so it's what you understood. It's the same operation, except the loss, the gradient is computed first with respect to parameters. This is good. This is well behavior, because you want to reduce the loss. You are going in that direction to reduce the loss. Reducing the loss means making the machine more intelligent. But if you change the input in order to increase the loss, that is adding noise to the input to fool the model. The loss is increasing. That means the mistakes are increasing. The mismatch between the prediction and the ground truth is increasing. That is what fooling essentially is. So yes, what you understood is correct. Such a small difference, people found out after training hundreds of models. People come up with this kind of a accidental discovery, I would even say, although it is not exclusively mentioned. But I strongly believe they might be trying out something else, and they might have accidentally found this, which is very important. Most of these scientific discoveries are accidents, some way or other. Anyway. All right, so this is one way, very simple way of creating attacks. Are there any other? Yes, there are a lot of such attacks which are proposed recently. A lot of groups all over the world are actively working on. I myself have created how many? Data free, yeah, NAG, triple F, yeah, 3 to 4 such attacks. All my papers in my PhD were finding out such vulnerabilities. Of course, we worked on the defense side also, how to handle those attacks. We worked 1 or 2 algorithms we proposed there also. But the essential fact is, it is easy to train attacks. It is easy to fool models. It is very difficult to train models to be intelligent. Somehow we achieved it. But at the same time, it is very easy to fool them also. We achieved that also. So that means, as I said in the previous session, current machine learning models are very intelligent, but are very fragile, very easy to break, right? So you can also try to come up with an attack. It is so easy. How? Basically, you need to create such technique with 2 things in mind. It has to be visually imperceptible. That means it has to be very small in magnitude. You cannot add a lot of noise. You cannot cover the entire object. Obviously, if you cover the entire object, the classification will be wrong. You don't have the dog to recognize there, right? You cannot add as much as you want. There has to be a limit on the noise that you can add. At the same time, mislead the classifier. The label has to be different from the original ground truth, right? If you optimize to respect these 2 constraints, so I'm talking about the optimization framework, where you have to have a couple of constraints. One is visually imperceptible noise to be added, and you have to add such a noise that misclassifies. Misclassification means increasing the mismatch between the ground truth and the predicted. So if you realize this too, you yourself can also create an attack. So all the attacks use these two constraints when creating the noise, right? So yeah, I have one more attack. So basically you can think of, let us say this is where your input sample is. This is class 1 to the bottom, and this is class 2 above the classification boundary, right? All that you need to find out is the distance between the boundary and the point. If you can add this distance, it will go from class 1 to class 2, right? So this is another way to fool. You have to find the boundary and try to add that perpendicular distance or the direction, perpendicular direction onto the boundary, and then suddenly after adding, this point will go here, and the class predicted will be different from the original class. So this is another way. 2016, it's called a deep fool, a very famous attack. People suddenly realized all these models are really not so intelligent. These guys are such as they were criticized to be stupid also, rightly so, because we want human like intelligence, right? We don't want machines that look at panda and say gibbon. No, we don't want that. So suddenly a lot of attacks came up and people started looking at simultaneously working on the defense side also. So let us try to understand why is this happening. A small noise when added is making the models to be stupid. So why do they exist? If you ask me the answer, it is not known. People are actively looking for answers to this question because mathematically they are very complex models with hundreds of layers, millions of parameters. You cannot simply write a mathematical function f of x is equal to this, right? In a polynomial form. You cannot write that. You may be able to write it, but it is very complex, and we cannot analyze it with the current knowledge that we have. So that is why only empirical analysis, only hypotheses have been created to answer this question. For example, as I said, one of the arguments is like we are using backpropagation, which is invented in 1960s or 70s. Even after 50 years, we are still stuck with that algorithm to train the neural networks. Maybe that is not the way to go about. We don't know. And another thing is we are projecting into high dimensions, 1,000 dimensions, 2,000 dimensions. So whatever training data we have, although it is 1.2 millions in this ILSVRC problem, it may not be sufficient, right? You have only points that are embedded in a huge space, right? It's called curse of dimensionality. Basically, with the increase in the dimensions, you need a lot of data to learn a classification problem. So that may be the reason. So yeah, these are all again speculations. People try to came up with these hypotheses, although they are not proven. Okay. Another thing is insufficient model averaging. Basically, the models are either overfitted or underfitted, but not rightly fitted. So that is another hypothesis. All the neural networks that are susceptible, they claim to be not rightly fit. So how to train to be correctly fit? Nobody knows. So this is only speculation. So another speculation is linear behavior. Although we have nonlinearities after W transpose X plus B. Nonlinearity can be, as I said, sigmoid, tan H, ReLU, any other nonlinearity. So theoretically, we do have nonlinearity. But maybe in spite of having nonlinearity, the function learned by these sophisticated models is maybe just linear. It is not really learning the capacity to learn nonlinear surfaces is another hypothesis. So there are a lot of such empirical evidences only. Nobody clearly proved why the adversarial perturbations exist. Not in the vision, not in the language, not in speech, nowhere. People identified, acknowledged it, yes, there is a problem we are working on, but trying to explain precisely why they exist has not happened yet. This aspect is now inviting or attracting more mathematicians to work in computer science, in machine learning, because obviously AI has billions of money now. A lot of governments and defense agencies, companies want AI to work. They want AI products to be sold. They want permissions to be given by the policymakers, right? Because of that, they are attracting mathematicians to look into this matter. Why is this happening? Can we find out and fix this issue mathematically? Computer scientists also have limited mathematical knowledge, but this requires thorough mathematical knowledge. That is where, the fields of computer science are now becoming interdisciplinary, attracting statisticians and mathematicians into the research in computer science. All right, so this is the gist. Why do they exist? Simply, nobody knows. There are a lot of hypotheses. Obviously, each of them is convincing. Everything may be right, but is it possible to fix any of these things? No, not at this point in time.
Excuse me, sir.
Sure.
So now we are creating noise by changing the gradients. Sir, do the noise naturally exist in the outside, sir? Because
Excellent. Yeah, excellent question. I must say, a very good question. So, yes, so far we have not come across this adversarial noise naturally occurring. For example, the models are being tested every day, 365 hours, 365 days, 24/7. People are testing these models by, conducting real world tests, autonomous vehicles, and not only autonomous vehicles, or other speech recognition models, everything. So monkey testing, all those testings have been conducted. Surprisingly, natural noise is not adversarial. Natural noise, these models are pretty robust to natural noise. For example, if you take some Gaussian noise and add it to image, it will be correctly recognized. This adversarial noise is very specific. Very specific. It will. I cannot say it will not occur in the real world. The probability to occur that is almost zero. Okay, that way the answer is yes. It is not natural, and we are only afraid because we cannot simply say this to policymakers, right? So we cannot simply say no natural process can cause this noise. Only attackers with bad intentions can cause this noise. If you say that, nobody's gonna take it for granted. We can't mathematically prove that also. So because of that, it is still an interesting problem. And more than anything, the easiness, the simplicity with which one can create this noise is more problematic. But natural acquisition, no. We haven't come across any such noises naturally. For example, we take photographs in all weather conditions, in moving conditions, on a vehicle. We can mount on a vehicle and take images, and a lot of noise can be intentionally added. Nothing is adversarial. Only this way of creating noise is adversarial. Yeah. All right. Okay. We understood there is noise. We understood. We don't understand why it exists. Okay. Is it possible to overcome them? Can we live along with this? Can we still go ahead training the models and deploy the models? So simple things like, after all, it is a noise. Why can't we simply use filters and remove it? Obviously, this is the first idea. Why can't we, reconstruct images, replace patches in the images with similar looking other patches which are clean? That is called reconstruction. Or can we, simply detect whether this image is corrupted, whether something has happened on the image? These things, yes. As I was answering, in a standalone setup, yes, doctoring detection may be possible, but in applications that require continuous access or processing of the data, it may be very difficult. And all these operations like cropping the image, blurring, filtering, JPEG compression, all these things are thoroughly investigated and found out to be unsuccessful in defending against them. Okay, so if you do JPEG compression, if you do image blurring, nothing is going to stop you from getting fooled. In spite of these applications, the noise still is able to fool the model. That is even surprising. So yeah, all these simple processings, which are very easy to do. Blurring and all you can do. So even in a continuous video setup, you can install algorithms to do these things, and they failed. For example, so you may think that a lot of noise is added in the background regions. We only need the foreground to get to recognize, right? So after foveation, it looks like this. Foveation is basically cropping to the object, right? That requires detection of the objects and all. But let us say you detected the object and you cropped it, but surprisingly even this is good enough to fool the model. So you remove a lot of noise, right? All this background portion which has noise is removed now. If you just pass on this portion also, it is fooling. The recent attacks are very strong. So you will be surprised. I'll show one or two attacks, how small they are contaminating. I'll show. So I don't want to reveal the surprise. So I'll show them. Right. So what is the gist? These empirical methods like blurring, foveation, cropping, JPEG compression are not going to help you. Even if you apply all of them, the noise is going to still fool you. So adversarial noises are getting stronger and stronger. So for example, initially, the first 2-3 years of discovery, it was the noises were very simple. The adversarial perturbations were not very sophisticated. So when you do zooming in, that was good enough to save from the noise. For example, if I go on zooming in, suddenly the correct label is popping up, right? If you see after some level of zooming in, let me just repeat. So initially red means it is misclassified. After zooming in, slightly I'm zooming in. After zooming into some level, the correct label, which is Toby Cat, is coming up. This was the initial case, initial attacks. But the recent attacks, you do whatever, you do 4 times zoom, nothing is going to save. The label is still wrong label. So that is the strength of the adversarial noises that exist these days. So I'm just showing only the face of the cat. Even then, the algorithm is fooling the network. 5 times zoom in also, the label is wrong. Ideally, what you think is, all the background is gone, a lot of noise is gone, only the face of the cat is shown. What is there to get confused? You may think like this, but still the noise is so strong that the classifier, CNN classifier, is fooled. So this is one of the 2017 attacks created from MIT and OpenAI. Anisha Thalia is the author. Yeah, so the gist is again, the attacks are getting stronger. The defense mechanisms have to catch them up, have to win the race against the attacks, right? So there is one recent defense mechanisms. Defense is the counter thing that you do to protect from your attacking, right? So there is one successful, I would say relatively successful. It is not completely successful. We are still adversarially susceptible. Whatever model we train today is susceptible, but there is reduced susceptibility, right? The fooling rate is not 80%, it is only 40% now, right? So that is achieved using adversarial training. So this is so far relatively successful training method to counter attack these attacks. So what is adversarial training? So basically, you create adversaries, you create such noise and show those noises to the model during the training itself. Remember, the attacking part comes only after the training. So far, that is what we understood. There is a trained model. Now I don't compute the gradient with respect to weights. Now I'll compute the gradient with respect to X, because now my intention is to fool the model. So why can't I do this during the training itself? Let us create adversaries during the training, and along with the clean samples, I will present the adversarial samples also for the training model, right? So this is how it looks. So this model is under training. I am still training the model. So my X is this input, label Y is sheepdog. Yes, I present this image. Now I'll apply FGSM on this. I'll create X star. If I present X star, this will say it is a paintbrush. It is not a dog because this is adversarial, right? I create during the training itself. I create FGSM, fast gradient sign method attack. So I'll create X star. As I said, this is a paintbrush to this attack, this CNN. But we clearly know this is not a paintbrush. This is still a dog, right? I want the model to see that it is still a dog. It is getting fooled to be believing that it is a paintbrush. So what I'll do, I'll take this. I'll say, no, it is not a paintbrush. It is still a sheepdog. You try to learn that. So I'll show this image also and tell it is not a paintbrush. It is sheepdog, right? So this is called adversarial training because I am introducing the adversaries during the training process itself, right? It is kind of, showing the difficult examples, showing or giving the difficult training data during the learning process, right? So you have to think like it is a hard training. During the training itself, you create adversaries and tell them this is not a paintbrush, this is still a sheepdog, right? So this is called adversarial training. This is I have simplified a lot of things. So the major idea is this thing. There are a lot of variants to adversarial training also. Ensemble adversarial training, gray box adversarial training. This is our work we did in 2018 from IAC. And then again, PGD, projective gradient descent. Yeah. Adversarial training from MIT. A lot of people have come up with small additions, making it a little better, but year by year. Is there a question? Okay. So this is, as I said, so far successful. It's not completely successful. Why? So, okay, let me tell you what is happening in the best adversarial attack, which is PGD adversarial attack. So even after 3 years from its invention, PGD adversarial training is one of the best defenses. So what they do is, they will again they'll during the training itself, they create adversaries and tell the model not to confuse. They train the model using the hardest of the adversarial samples. So this is what they do. Within the surrounding of that X, they'll create the hardest example. Hardest example means where the loss is increased to the maximum, right? You remember, fooling is increasing the distance between predicted and the ground truth, right? Within the surrounding of that X, they'll create X star where the loss is highest. So that way fooling is maximal, right? They create that X star where the discrepancy between predicted and ground truth is more and use that to training. So this is very intuitive, right? So keeping the math apart, it is very natural. Yes, if you give the toughest of the samples to train, obviously the network will be very intelligent, right? So that is what PGD adversarial training does. Within that delta, within the delta ball, they create the toughest adversaries where the loss is maximized, right? Where the discrepancy between the so that is worst case adversary. So every time you train a sample using a sample, you create this sample also and tell the model not to confuse. So that is what is happening in PGD adversarial training, which is by far the best defense. So why do I say by far? This is how the accuracy is. For example, on natural images, clean images, the classification accuracy is 87.3. Okay, this is a 10 class classification, cipher 10. That means there are only 10 labels in the classification problem. So after FGSM, the accuracy will be down to 56%. FGSM is the fast gradient sign method, creating the gradient and then adding the gradient with epsilon, right? So the PGD adversarial attack is 50%. But the PGD adversarial training, what I just described, it will bring the accuracy to 64. So 87 is the natural clean accuracy, but the adversarial accuracy is 64% only. So what that means is Even on the adversarial samples, 64 times it is correctly classifying. Ideally, I want 87 because that is what it is predicting on the natural samples, clean samples. But still there is a gap. 23% gap is there. That means PGD is effective to some extent. It is not 100% the solution. So that is how, that is what the state of the affairs is. So again, a lot of efforts are going on currently. We are also trying to come up with models and algorithms that train the models effectively. Um, the gravity of the problem is very important, very huge. So as I told you, every model that uses deep neural networks is susceptible. There are hundreds of areas in which deep neural networks are deployed. So all of them, because nobody is attacking, they are safe. So also, so far we haven't come across any natural way of occurring that noise. But we never know. Maybe there are some natural processes where these noises can come up. So far, we haven't come across. No algorithm, no work has reported natural occurrence of such noise. All of them are man-made efforts. We intentionally created that noise because you never know. Some competitor companies may create them and attack yours. So you need to be aware of that literature. So because of that, a lot of people simultaneously are attacking and trying to defend them so that the field goes forward in forward direction. All right. So yeah, let me just finish the adversarial training. But the biggest drawback of adversarial training is it doubles the training time because every time you create, because every sample you need to create X star and then show that it is not a paintbrush, it is still a dog, and do this. Essentially, it is multiplying the training data, right? On the clean data, you have to create adversaries and then train the network. So this is very complex. Training time, the power, everything increases and it gets multiplied, right? You see why? Because every time you need to present a clean sample, you have to create adversary and then show that also. And you may need to do this multiple times, and you may have to do this with multiple attacks also. So there may be multiple ways of creating X star, not only one way. PGD does it one way because they believe they are doing it with the worst case adversary. This is the toughest adversary, right? So they are doing it iteratively to do this. So it's computationally very expensive. And imagine training with millions and millions of images. So currently, there are a lot of companies that train the models day and night, 365 days. Now, because of this adversarial training, things get double or triple difficult. So that is the drawback. So, but what do we do? That is the best we can do, right? Also, it depends on the attack that we create. So X star can be created in multiple ways. Let us say you created an adversarial training based on your attack. I created adversarial training using my own attack. So will there be um, coherence between your method and our method? Not guaranteed. Your trained model may be robust to your attack. Maybe there may be transferability to some extent, but not 100%, right? So it may be susceptible to a different adversarial attack tomorrow if something comes. So all of these problems that are existing, that are open in this area, even today. So yeah. Yeah, as I said, this adversarial training may be specific to attack. So one observation is PGD so far is very good generalizable. So PGD, when you attack with FGSM or if you attack with other deep fool, it is showing very good accuracy. So far, so independent of the attack, the accuracy on the adversarial samples is good for PGD. So that is why I'm trying to spend some more time because of the importance and the significance of the method, PGD method. All right. There are multiple ways. So a lot of mathematicians also as I said, started to work on this, and they tried to propose, maybe the model is not continuous. The function learned by the neural networks is not continuous. At times, it is discontinuous. So we have to include um, training algorithms that make it continuous. So we are bringing the concepts of continuity of the function, differentiability of a function into learning these models. So there are a lot of such works which are promising directions, but they fail to scale to bigger networks, bigger problems. So that has been the case so far. So what happened is on small networks, small problems, people show to learn continuous functions with very well behavior, such as smooth predictions within the neighborhood of the data. All these things will be sufficiently learned in case of smaller neural networks, one layer neural network, two layer neural network. They will show on toy data sets. But effectively, when they try to implement for real world problems, not even real world problems, difficult problems than the toy problems, that itself, they break their algorithms. They do not really generalize beyond those toy examples. Of course, we are talking about very initial days of the field. Deep learning is hardly 1-2 decades old. So obviously it takes a lot of time for any scientific field to get matured. Now that there is a lot of interest, things like exaggerated, the things look exaggerated in this area, but obviously we are hopeful. A lot of enthusiastic scientists and grad students are working together to make these models more and more reliable and more interpretable also, right? Because any simply as a paintbrush, but we need some feedback. We should be able to ask what makes you use a paintbrush. Can you point out the region in the input that make you believe this is a paintbrush? So this is called interpretability. You need to be the model has to be able to answer why it has predicted. What is it? For example, paintbrush is what is predicted. So you should be able to show some regions. So because of these regions, I believe it is a paintbrush. So that also not very well. It's not mature in deep learning as of now in the current AI systems. So another direction in parallel is realizing interpretable models, learning interpretable AI. So that's helpful, right? For example, it finds out the reasons why this is a paintbrush is some sort of a fixing mechanism. It's not looking at those regions and try to come up with training procedures that are more sensible than this kind of stupid behavior. So that is what's happening in this area. Um, as I said, adversaries are getting bigger and bigger, stronger and stronger. For example, this attack, which came in 2019, is called a single pixel attack. It is ridiculous. They change only one pixel value. And from cup, it becomes a soup bowl. Of course, they're semantically closer. Cup and soup bowl look very similar, right? But the label is different. Cup is a different label. Soup bowl is another label in the 1,000 categories. It is insane. All that they did is changing one pixel value. One pixel value, not even 10%, 5% pixel values. Here also, only one pixel, which is shown in the red circle on the face of the baby. So initially it was basket. Basket is the basket in which the baby is sleeping. That is the label. The system identified with 16% confidence that it is correct label. But now after changing this one pixel, suddenly the same model simply says it is a paper towel. So this is a big problem, right? So far we were thinking about adding noise, which is spread over all the pixels. Of course, it is limited in magnitude by epsilon, but it is still stronger because it is changing all the pixels. Just 1 second, please. But now, single pixel attack,
Excuse me, sir.
please.
So what that noise contains, sir?
So noise means, adding or subtracting some value. The pixel values in this image are 0 to 255. Let us say this is RGB image. You will have RGB, three values. You're just, it depends. It depends on the image, obviously. But noise is basically, minus 100, plus 122, plus 77. So these are some example noises I'm giving you. If I just add those values to the existing values, that is attacking. That is one noise, one possible noise. Noise means, it's a signal which is not meaningful, which is not intended to be meaningful. Right?
Thank you, sir.
Did I answer your question?
Yes, sir.
Yeah. So noise means it's nothing. It's just, some value which is not meaningful, which is not intentional. I just randomly add something. But random noise is not fooling. Structurally, carefully crafted noise is only adversarial in nature. So they come up with such a strong noise, which when added to one pixel in the whole image is able to fool the classifier. So yeah, so there are a lot of such attacks. For example, let me cover some more. So Google in the US also, they investigate, or they research about driverless cars. In fact, because it is not legal anywhere in the world to actually drive driverless cars, what they do is they, within their campuses, within their warehouses, within their operating environments, they are driving for at least 4 or 5 years now. They are driving driverless cars in the US. So they do a lot of this research. What they did, they have created 1x1 patch. So just imagine a stamp, a postal stamp kind of thing. So they went on posting on the signboards within the campus, within their testing environment, and the vehicles got fooled. So small noise, which is pasted on the corners, not even in the middle of the signboard, only towards the corners, which is almost nothing, 1x1 inch patch, right? Which is only 1 inch by 1 inch noise. You just randomly create, not randomly again. So carefully crafted noise of 1x1 inch. They pasted on the signboards, and they found out that the vehicles got fooled. They are behaving abnormally. They read the signboard wrongly, and because they are reading wrongly, they behave wrongly. They take wrong actions. So these are all practically verified. And another thing is, because there is a lot of acquisition noise, non-linear operations happen, right? So for example, I paste something on the board. A camera has to look at that signboard and then take a photograph. Then there will be compression happening. There may be a lot of noise in the camera sensors. Because of that, whatever noise I added may get modified, right? I added, let us say 100 I added, but looking through another camera, also different times of the day, right? Afternoon times the brightness will be high, mornings and evenings the brightness will be lesser compared to. So different operating conditions may read the noise differently. Different cameras also, a Motorola camera versus a Nokia camera looks differently. The pixel values will be similar but not identical, right? So depending upon the sensors you use, depending upon the day, the time of the day you capture the image, a lot of changes are there. Despite all those changes, this noises still fool the model. That is even surprising, right? So I created with one model in mind, and some other model comes with different sensor statistics. Still, this noise is able to fool, which is really dangerous, which is really important to look into. So that is what is happening. For example, another application is object detection. Object detection means you have to find the object and draw a bounding box. Find means classify it. For example, this is a horse. You have to draw a bounding box to the horse and say it is a horse. And another person is there. You have to draw a bounding box and say it is a person. So that is called object detection. That is a important computer vision task. So because some noise is added, the model is looking at background regions and predicting what is it predicting. Yeah, I'm not able to see the labels, but it is clearly predicting locating in the background. There is no object here. There is no object here. So what it means is not only classification, other computer vision tasks are also affected with the added noise. You can clearly see the noise here is added only in the top left corner. I hope you see the noise patch here on the top left. Because of this added noise, everything is getting messed up, right? The bounding box, which is supposed to be here, is moved here, and I don't know what this is. This may be horse. This is person. The first one is person. This may be also person. So the the summary is because of this added one cross one or some patch, noisy patch, the algorithm fails to detect correctly. So which is again very important or very dangerous thing. So because if it is recognized and you proceed, obviously a lot of downstream tasks will be dangerous, catastrophic also sometimes. Yeah, these are called patch based attacks. This is single pixel based attack. These are patch based. So this was similar to the experiment that I've described with Google. Right. So yeah, these are some of the adversaries. There are a lot more of them. So yeah, so there are a lot of surveys also available. Just to summarize what kind of attacks are available, what kind of vulnerabilities are discovered about these models. All those things are available. So fooling rates are as high as 70 to 90%, and even 100% also sometimes are there. So we need to be really careful. That is one thing. All right. So, what do we conclude from all this discussion? Right. So, let us try to summarize what we understood in this two sessions. So, what we started with is yes, machine learning and AI, deep learning is really significant. And in terms of advancements, it has created a lot of products. Yeah. So for example, I have given a lot of examples, but let's recollect. So Google uses a lot of AI, a lot of deep learning. Facebook, Microsoft, Amazon, everybody uses a lot of AI solutions. Yes, we are using a lot of machine learning and AI solutions in our lives. So how do we achieve it? We have a lot of data, we have a lot of compute, and we have gradient descent, we have backpropagation, we have neural networks. The gradient is the key in learning neural networks. So I strongly encourage you to take a look at the backpropagation and gradient descent again. Those are the very fundamental blocks to neural networks and deep learning. So gradient is helping us to train the model. You remember dou j by dou theta. That is the key. You compute the gradient with respect to the weights and move in the negative direction. That is training. But if you compute the gradient with respect to x, dou j by dou x, and move in the direction of gradient, it is fooling the model. It is completely doing the opposite of the training, right? So gradient is a double-edged knife. We trained using gradient, we attacked using gradient, right? So gradient is very important. Gradient is everything. Gradient is the god in deep learning. Okay, so you need to understand the gradient completely, and it has both positive effects and negative effects. If you use it accordingly, it can do wonders. So that is one take home point. So adversarial perturbations are definitely intriguing, very interesting, very shocking discovery of machine learning and neural networks. We have to understand them, why they exist. Of course, a lot of theories are coming up, nothing concrete, nothing mathematical, no proofs, only hypotheses and speculations are given, and a lot of empirical it is very active in that perspective. It is very, very active, and we need a lot of participants, a lot of young blood to be investigating these aspects, because as I told you, a lot of our decisions are made now by AIs, starting from loan rejection, loan acceptance, credit acceptances. Even US courts use AI to grant parole or bail to the um, prisoners, right? It is happening not just now, already from for some years. They are using AI based application processing for paroles of the prisoners. Whether to give parole or not to give parole is decided by AI. Lot of such important decisions in human lives are made by AI. So we need AI to be very robust, very strong, very reliable, right? So we have to build such systems. Today, yes, we understood models are performing well, but they're easy to break also. So that aspect we need to fix. Again, we need rigorous understanding about the models, the training mechanism, and everything, the whole perspective. So we need to bring in a lot of other aspects also, which I did not cover. For example, fairness. We need to avoid biases in the training data. Sometimes biases in the training data also cause some side effects. So some other time, if I get a chance, I'll try to describe. But all these factors come into play, and we don't know how they interact actually also exactly. So it's a very complex thing, but obviously we are making step by step progress. Sometime soon we will be able to learn and deploy models that are robust like humans. All right, so this is what I had. I can now discuss, and any questions or anything like that, then yeah, I'll be more than happy to discuss.
Sir,
Sure, I will be sharing. Yeah.
sir, can we call this in the backdrop of this adversarial in this one? The neural networks fail to understand the features of the any objects.
Um, so yeah, yes, you can say that, because uh, if it understands features really and accurately, it should not be fooled. Yes. So in fact, if you see, you're still able to see my screen, right? My slides.
Yes, sir.
Okay, okay. So one of the very recent hypotheses, 2018 or 2019. So let me, yeah. So predictive accuracy versus robustness. So what they say, similar to what your opinion is, what this work says is, so neural networks learn features that are important for accuracy, not for robustness, right? There is a difference. There is a different set of features to be robust, and there is a different set of features for accurately predicting it. Because they are learning these features, they are missing robust features. They are not able to learn robust features. So this is exactly what you pointed out. They are not able to learn features that are responsible for robustness. Correct. So they are only learning features that give better accuracy on clean data. On clean data. Correct.
And
Hello.
one more thing, sir.
Yes.
We are only fooling the machine only in the image processing, sir, not in other areas of the AI, sir.
No, no, no. We are. Let me go back. So I only covered this application. For example, I showed a review, right? A movie review, where changing the word from footage to film to footage. Yeah, here. So this is an adversarial example in text. So I change this word C to A, or I change the film to footage. Suddenly the classification from positive it went to negative. So this is also fooling the text model, the model that is classifying the text. Similarly, automatic speech recognition also. So Alexa like models, they understand what I say, right? if I add some noise in the background when I am speaking, they recognize the words wrongly and behave wrongly. So that is also demonstrated by Stanford group. So adversarial perturbations are there in all the AI fields, computer vision, speech processing, language processing, or if there is any other application, there is quite some evidence to believe adversaries will exist even that application also.
Thank you, sir.
No problem. Pardon? Please go ahead. He can ask.
Hello, sir.
Yes.
Sir, I am having one question, sir. If I build a model, during the training process, I split my data sets into training and validation. Suppose if I am getting my training loss is very high compared to my validation loss, so what it says, sir, actually, how I can minimize the loss, sir?
So let me repeat. So during the training process, your training loss is higher than the validation loss. Is it
Yes,
right?
sir. Yes, yes.
So what is the question? So how to avoid that or why it is happening?
Yeah, sir. What's happening? What are the things? What are the necessary steps I need to take care of that to in order to minimize my training loss?
Right. So it clearly tells you that the distribution of validation loss and the training loss. Sorry.
Yes, sir. 80 into 20% is I splitted, sir.
True,
80
true, true.
percentage.
Yeah. Yeah. So so when I say the variety in the validation loss and the variety in the training loss are different. If it is same, if it is similar, the loss behavior will also be similar, right?
Okay.
So what you need to do in these cases is you have to do cross validation. Leave one out cross validation or leave some cross validation. What you do is every time you pick different 20%. Okay, so you can
Yeah.
take first 20%, second 20%, third,
Yes.
and so on. 5 20% you can take and take the average. In that case, it will be similar.
Okay, sir.
So this is
Is any other? I tried in that way also, sir, but still I couldn't able to improve my accuracy. So that's why
okay.
I'm asking: is there any other methods is available to overcome those last failures, sir? That's why I'm asking. I developed the LSD model. I faced the for prediction problem. I faced this one, sir. Issues. That's why I'm asking, sir.
This is very strange. Generally, validation has to behave similar to training data, except that you don't train on them.
Yes.
Um, loss, that's why it should be at least as less as the training loss. It cannot go further below.
So always our training accuracy is more compared to your validation accuracy, na, sir. Is it that line? My line is correct, sir.
Say it again, please.
Sir, my training accuracy should be high compared to my validation accuracy during my training process. Is that, sir? Is that any ground rule is there, na, sir?
No, the training accuracy should be lesser.
Okay.
Yeah, always the training accuracy has to be lesser because the model is shown the data. The model is continuously looking at the training data and learning from the training data. It has to at least memorize it.
Yes.
Yeah. So validation is new data. It may create some problems. That is why the loss there can be more.
Okay.
Yeah. The loss on the training data has to be always small.
Mm. Yes, sir.
So I'm not sure what is happening. Maybe there is some discrepancy between the validation and the training, or maybe
Okay.
some issues with the training also. Yeah, you have to carefully look and debug. Maybe it's some issues with that.
Okay, sir. Thank you, sir.
No problem. Thank you. Thanks for giving me this opportunity. I hope I have given you a decent idea about uh, the adversarial perturbations, adversarial noise things. This is very recent developments in the field. So don't feel frightened or don't feel unhappy if you had not understood completely. Yeah, the slides I will be able to share. Yeah, this is very active area. So if there are any PhD students, or if you have any PhD students with you, please try to encourage to pursue research in this area. There are a lot of resources. You can visit my website or other people's websites who are working in this area. A lot of active things are happening. So I strongly encourage you also to enjoy this kind of research. Yeah. So thank you. Thank you. Thank you. You too, sir. Thank you.
Yeah, good afternoon. Thank you.
Good afternoon, sir.
Yeah, good afternoon. Yeah. So can you hear me? Please confirm and whether you can see the slides. Okay.
Yes, sir, it is visible.
Hmm. Okay. So thank you so much for inviting me to this event. And yeah, thanks a lot to all the organizing team for the wonderful organizing this event. So I would like to deliver today's talk on large scale support vector machine algorithms. So essentially, I'll focus on four different topics. So I'll start first what exactly is support vector machines. We'll try to explain geometrically and theoretically. And then we'll discuss mainly you can see what is least square twin SPM, what is improved twin SPM, and then three proposed model based on large scale algorithms. So it is based on least square, based on using pinball loss functions, and based on a fuzzy concept, especially for class imbalance data. So here, since I would like to start first, what exactly is SVM? So I think let me just give first the outline of support vector machines. So could you please just let me know what is the background of the participants here? So are they aware of means all are computer science background, or they have different backgrounds, not aware of machine learning? Organizers? Hmm. So all these participants have the background of machine learning. Okay, very good. Hmm. So essentially here my objective just give the quick idea what exactly is a stream, and then we'll move to the advanced algorithm. So please try to understand. You can ask me questions so that I can give answer immediately. Then we can proceed for the next means the main session. So support vector machines being computationally powerful tool for supervised learning, initially introduced for classification problems, and then by the same team it uh, extended for the regression problems, then also later for clustering problems. And nowadays, if you look at the applications, it has been applied almost in all the directions. I have mentioned a few: particle identification, pattern recognition, bioinformatics, and you can see about the cancer classification, Alzheimer's disease predictions. Almost, if you look at electrical engineering or biomedical engineering, computer scientists, even mathematician, physicists, even chemistry, almost all the peoples are just using for as an applications of SPM. So nowadays there are many advanced algorithms, especially the most emerging is deep learning. If you are working on large scale data, then yeah, you can move in that direction. because if the data is large, so then your performance will be high. So now here in support vector machines, the basic idea is to find out a best hyperplane, optimal hyperplane between positive and negative samples. If we are talking about binary class problem. So this is the first this objective to find out the best hyperplane between uh, positive and negative samples. So let me just give an example. If you look at this figure, and we have two different kind of data. So different kind of dots, and the idea is how to classify this kind of data. So it's very simple data, linear data. So if you draw a line, so you can see that the data points are classified. So here, as I mentioned, the objective of support vector machine is to find an optimal hyperplane, best hyperplane. So this line is the best hyperplane, means best classification line. So because if I draw another line on the same data, so it is also perfectly classified, this data. So there are maybe another line, there may be n number of lines, so that can classify the same data. So here the question is at which line is best, which line is optimal. So the first idea is coming of SVM is called maximizing the margin. So now sometimes it happens the data points at the time of this draw, this hyperplane. So some of the data points may lie on other side. So it is called misclassification. So we usually do it, we'll discuss later on. We just penalize such kind of classification points and then add on the objective functions. Uh, so now here, in general, the first property is maximizing the margin concept. So what exactly is margin is nothing but the distance between this positive and negative samples, such that this distance is maximized. This distance is maximized between positive and negative samples. So you can here look at it that if I have two different kind of data points and we just maximize this distance between positive and negative samples. So you can look at the here green this lines. So you can see that the data points corresponding to these lines is called support vectors. So why we call it support vectors? Because these are the vectors that support or that decides the decision hyperplane. You can see here the middle one, exactly the middle one is a decision hyperplane. So, this is the first property of SVM that we just maximize the margin. If you can look at mathematically here, you can see here w dot x plus p. This is greater than or equal to 1. So we have the upper class and lower class. This is w dot x plus p equal to minus 1, or you can say less than or equal to minus 1. So data points which lie on the lower supporting hyperplane or below this. And the distance between these two is called maximizing the margin. So with the distance between the hyperplane, so just a very simple formula, we can always write 2 upon norm of W. So we are essentially maximize it. So maximize means 2 upon norm of W and subject to the constraint. What are the bounding conditions? That the data point should either lie on the hyperplane w dot x plus p equal to minus 1 or below this. And data point should lie either on w dot x plus p equal to 1 or above this. Right? So then the distance will maximize. So we are essentially maximize this distance. That is, we are maximizing 2 upon norm of W subject to these bounding conditions. So you can see that if there is a misclassification points, so we just penalize those misclassification points. We sum up in we sum up all those misclassifications, and we penalize with the parameter C, and we add it. So here parameter C is nothing but to control the overfittings. So you can just see that what is the difference between a hard margin and soft margin. So the only difference whether we are just properly classified or there are misclassification. So if there are misclassification, we usually call this soft margin. So now it's very important here to highlight this one. So here, if you we'll discuss also this in more detail that how this dual problem is coming out. So this is the dual problem you can see here, and in this dual formulation, what we see that the data points appear in the dual formulations in the form of inner product. You can see that xi transpose xj are appearing here. So it means that it will help us in the case of nonlinear data, because for linear is quite simple, but we'll see how to handle the situations when the data is nonlinear. So now you see here uh, the first example, the data sets that are linearly separable with some noise. So you can see we have blue and red dots. So in the real line, if you just draw a line in the middle, so you will see yes, it's linearly separable, no problem. But if you look at the second column, we have red dots, blue dots, and red dots. But if you draw a line, we cannot classify red and blue dots. So in the real line, in R, in one dimension, we cannot classify. But if you slightly modify in the sense that if you map the same data in some high dimensional space, means if you just map in R2, that is in plane, so you can see that this data is linearly separable. So it means that we just map our real line to plane, okay, and you just assume fx equal to x square, right? So it's a parabolic situation. So in that case, what will happen? Data points will move up, right? So when we'll move up, so then you can see that we can draw a line in the middle of blue and red dots. So this is a very simple example just to understand the problem, but this is not the situation every time. That if you have the data points in R, so you can classify in R2. It may not classify in R2. It may classify in some more higher dimension, right? So for example, if you look at it, so we cannot draw the left side. If you look at highly complex data, there's red points and blue dots. So we cannot classify here. We are in R2 in plane, but here we cannot draw a line in the middle of blue and red dots. So it means that we have to move some high dimensional space, right? So here the more general idea is the original input space can always be mapped to some high dimensional feature space such that the training set is linearly separable. how to map it? So we just use a map file to transform this data in some high dimensional space. Okay. So usually we called this kernel trick. So okay, so let me just give some background. So if you just recall the linear classifiers, so that relies simply on the dot product, that is xi transpose xj, as I pointed out in the case of dual column of the linear formulation. So the data points appear in the form of inner product, that is xi transpose xj. So we are just writing here just represented as k xi comma xj. But if the data point is mapped into some high dimensional space via some transformation file, so in that case, the dot product becomes phi xi transpose phi xj. We just represent k. Okay, and here k is nothing but a kernel function that corresponds to an inner product in some high dimensional space, expanded space. You can see that with one example, if I have a vector x and we are just writing k equal to 1 plus xi transpose xj square, so we can always write in the form of phi xi transpose phi xj. Okay. So there are several kernel functions available in the literature. So this is a natural problem in the machine learning algorithms, especially SPM, that very difficult to say that Gauss, this particular kernel is suitable for all the kind of data. No. So people are just using different, either trying to do the numerical experiment, do the whole analysis with different kernel functions, and another way doing ensembling, weighted ensembling, and multiple kernel theory. So several research are going on. So here my focus is not on that theoretical aspect of kernel trick, but theoretical aspect on the development of the algorithm. So you can here look at for the nonlinear formulation for the case of SPM. You can see here the dual formulation. So you can see that in the dual formulation in the form of xi transpose xj. Here we just replaced with the k, that is phi xi transpose phi xj. So this is the only difference, and advantages at the same time that we are dealing with a large scale, highly complex data, but we are efficiently working in SVM for the complex data. We just replace with K, and K is some kernel, and many kernel functions are available. We just use and proceed. And it's quite easy to work in MATLAB or Python. Codes are publicly available in all library. So you just use it directly with your data. So if we look at the overview, SVM locates a separating hyperplane in the feature space and classify points in that space. And it doesn't need to represent a space explicitly, simply by defining a kernel function. Here, the kernel function play the role of the dot product in the feature space. Okay. So, in case of any question, you can ask me. I'm happy to answer. So far I just try to represent some geometrical aspect, and now I'll try to explain how the people are working theoretically in SVM. So you can see here linearly separable problem. So let us consider the training set T. It is x1, y1, x2, y2, xl, yl. here x1, x2, xl are input points, and here yi's, that is y1, y2, yl, they are corresponding outputs. In case of binary, we just say either class 1 or class minus 1, or we say class 1 or class 2. So the idea is that of the SVM, we just need to search for the separating hyperplane, that is W transpose X plus B. This is equal to 0. And as I explained about the maximizing the margin concept of SVM, that means that we are simply maximizing the margin between the positive and negative samples, that we are writing 2 upon norm of W, and we can also say that equivalently there is a minimization of the regularization term 1 upon 2 norm of W square. So this separating hyperplane W transpose X plus P equal to 0, it lies exactly in the middle of positive and negative this bounding hyperplanes. W transpose X plus P equal to plus 1 and W transpose X plus P equal to minus 1. So, and the data points which lie on the planes or supporting hyperplanes are called support vectors. So this is more clear picture that we have two class data points, and this black dots and simply this white dots. So we just say that the data points which lie above W dot X plus P greater than or equal to 1, this is corresponding to class plus 1, and W dot X plus P less than or equal to minus 1, it is corresponding to the data points of class minus 1, and the distance between these two hyperplanes is called 2 upon norm of W, that is called margin, and the middle one, that is W dot X plus P equal to 0, this is an hyperplane. Okay. So now this is the primal form of the support vector machines in the case of soft margin, linear SVM. Okay. So here you can see the first, this is to minimization of half norm of W is square plus C here is a parameter that control the overfitting. Summation xi is a slack variable, that is misclassification error, and here yi is nothing but plus 1 or minus 1, okay, either in the class 1 or class minus 1, and here W transpose X plus B, this is greater than or equal to or less than or equal to 1 minus xi, so this is the corresponding hyperplanes. Okay, so we have here one objective function and two constraints. Two constraints how? One is corresponding to class plus 1 and one is corresponding to class minus 1. So here the point is I have this optimization problem and how to solve this kind of optimization problem. So I have an objective function subject to the constraint conditions. So I'm going to discuss the more general, not specific to the SVM, but the in general for the optimization problem. So then I'll come back how to solve this linear SVM problem. Okay, let's try to understand how to minimize an objective function subject to the constraints. So suppose we want to minimize a function fx subject to the constant gx equal to 0. So the necessary condition for x0 to be a solution such
Yes, my
that,
dear.
yeah, any problem? Anyone?
No problem, sir. You please go ahead, sir.
Okay. So since I'm just trying to explain an optimization problem, how to minimize a function subject to the given constraint, and then that constraint is equality, that is gx equal to 0. So the necessary condition for x naught to be a solution such that the condition, that is partial order derivative with respect to x of fx plus alpha gx at x equal to x0, this should be 0. And the second is gx, that is a constraint, gx equal to 0. Here alpha is Lagrangian multiplier. So suppose I have multiple constraints, that is G1, G2, Gn. So then we just modify these necessary conditions. We just take the partial order derivative fx plus summation alpha I gix. That is alpha 1 g1x plus alpha 2 g2x plus and so on alpha m gnx. This is equal to 0. So this is the way for the case of equality constraint. For example, if I have inequality constraint, then how to handle the problem? I mean, if we have an objective function fx and subject to the constant gix is less than or equal to 0, how to optimize it, how to minimize it, this function. So in that case, there must exist Lagrangian multiplier alpha I such that x naught must satisfy these conditions: partial order derivative fx plus summation alpha I gix is equal to 0, and the inequality constraints. And in this case, fx plus summation alpha I gix is usually called Lagrangian function. And then we simply set it to the gradient to 0. That is del L. Suppose if I just write L equal to fx plus summation alpha I gix. So then we just take the partial order derivative del L over del x, del L over del alpha, and so on. Whatever is given to us, we equate to 0 and then solve it. For example, let me just come back to this problem. This is what we were trying. So we have this minimization problem, inequality constraint. We just write what is L, then take the partial order derivative, equate to 0, then we solve it. Let's see what it will come. You see, for the linear SVM case, I just write first the Lagrangian function. And here we just write alpha, beta or Lagrangian multipliers. So we just take the partial order derivative with respect to w, b, and xi, just using the KKT conditions. Finally, we get the dual formulations. So you can see in the dual formulations, the data points appear in the form of inner product, that is xi transpose xj or xi transpose psi. So just remember this. So what will happen in the case of nonlinear data? So in place of this inner product of this input data, so we'll see what it will come. So okay, so usually what happens in the case of this kernel functions means when we are dealing for the nonlinear case, so kernel should satisfy the Mercer theorem. So you can just go through this as a basic theory behind it, so that the function is positive definite, and there are many kernels available in the literature. So let me just try to explain how to solve the problem for the case of nonlinear SVM. So you can see here, I hope that it will help us to understand another some proposed idea that we tried to align with the SVM. So you can see this problem and the previous linear SVM problem. So the only very small change here, in place of xi, W transpose xi, we are just writing W transpose phi xi. Rest is same. So we just write the Lagrangian functions, take the partial order derivative, equate to 0, and finally we got the dual formulation. You can look at it, the dual formulation is coming phi transpose phi, right? And phi transpose phi is nothing but some k, kernel, okay? So essentially, what is the benefit of doing it? Because it's a great advantage of support vector machines to handle a very complex data. So how? Because we are dealing very large dimension, highly complex data, but we are working in linearly. Because you can see that here kernel is nothing but is an inner product. Inner product is nothing but just a number. Okay. So you can see benefits. The training is relatively easy. No local optima, unlike a neural network. It scales relatively well to high dimensional data. And the trade-off between classifier complexity Hello.
Yes, sir.
So I think my lecture was disconnected. Looks like to me.
Yes, sir. Yes, sir.
When it was disconnected just now.
Yes, sir. When you are explaining about that phi of xi, replacing with phi of xi and advantages.
Okay. Then great. So just please confirm. Maybe some problem. Yeah. That's fine now.
Exactly. Yes, sir.
Okay.
Sir, can I ask you a small?
Yeah.
Sir, what exactly is this phi of xi? Do you define a new variable here?
I think I explained initially what is phi. Let me just. Yeah. You see here. Phi is nothing but is a map, like is a function.
Okay.
So that transform input data in some high dimensional space. You can see here we just transform this data from plane to 3D. So it could be means here R2 to RD. So D could be or I can say that more general, that phi is nothing but from Rn to Rm. So and the right side Rm where n is greater than n.
Okay.
Okay.
So that can be generalized, sir, or it is specific to the problem or distribution of the data.
This is more general. This is more general. Whatever be the complex data you have, so you can see I explained I try to explain in more better way that whatever be the complex data you have, but we are dealing just linearly. We are dealing a very high complex data, non-linear data, but dealing linearly. So how? Because of this kernel trick. Because what happens when you just transform this data? So the advantage is that we are working in the nonlinear case in high dimensional space, but you see that we do not need to know about the nature of phi. You can ask me what is the advantage of phi. So the advantage of phi is nothing but just to make the formulation more simpler. So because to solve our non-linear data, very high complex data, so we are just uh, calculating the inner product, right? So, and we do not need to know about the nature of phi. We do not need to know about the dimension of phi. We don't need actually. So the reason is we just need the inner product, just dot product in high dimension space. So this is the advantage. Means we discuss maximizing the margin and this kernel trick. So these are the major advantages.
Okay, sir. Thank you.
So now I'm trying to move to a new problem is called moving ahead twin support vector machines. So this is the first effort in 2007 by Jayadeva Khemchandani and Suresh Chandra from IT Delhi. So they developed this algorithm for classification problems. So, and after a few years, a lot of improvements in the case of classification, regressions, clustering. So, and all theoretically improvement has been done in this direction. And nowadays, it has been applied almost in all the directions. So you can see that people have written several last 3-4 survey paper. Uh, my group already have written one survey paper that contains, I think, more than around 300 papers of Twin SVM. So, and this Twin SVM paper published in IEEE PAMI, it has, I think, more than 1200 citations. So, if you are interested in this direction, it's really nice. Uh, so let me just try to explain this formulation. So, what is the idea behind this twin support vector machines and how it is implemented? So, twin support vector machine is computationally more efficient model than support vector machines. So, essentially, in twin support vector machines, it determines two non-parallel planes or non-parallel hyperplanes instead of a single hyperplane as we see in support vector machines. So, and we are simply solving two smaller kind of support vector machine problems, each of which is smaller than conventional SVM. So it makes twin SVM approximately 4 times so faster than SVM. So, and this twin support vector machine has been implemented several real world benchmark data set, and we see that it is not only fast but shows better generalization performance, and it is also useful for automatically discovering two-dimensional projection of the data. So let me just try to explain the formulation. So you can see that Jayadeva group this introduced a novel approach in 2007. So that is called twin support vector machine, that is called TSVM or TWSVM sometimes. So what happens, they obtain non-parallel hyperplanes around which the data points of the corresponding class get clustered. However, they are based on entirely different formulation. In fact, each of the two quadratic programming problems, and you see in equation 1 and equation 2, so they are typically a SVM problem, except that not all patterns appear in the constraints of either problem at the same time. Okay, so you can see that 1 and 2. So this is the pair of quadratic programming problems. So essentially, the twin support vector machine algorithms finds two hyperplane, each one for each class 1 and class 2. Okay, and this classify points according to which hyperplane a given point is closest to. The first term in the objective function of 1 or 2, equation 1 or 2, is the sum of squared distance from the hyperplane to points of one class. Therefore, minimizing it tends to keep the hyperplane close to points of one class. For example, we say class plus 1, and the constraint require the hyperplane to be at a distance of at least 1 from the points of the other class, say class plus minus 1. And the second term of equation 1 and equation 2, we have a set of error variable is used to measure the distance. Means we are just minimizing the sum of error variables, thus attempting to minimize misclassification due to points belonging to class minus 1. So essentially, this twin support vector machine algorithms comprise a pair of quadratic programming problems, such that in each quadratic programming problem, the objective function corresponds to a particular class and the constraints are determined by patterns of other class. Thus, twin support vector machine gives to two smaller size SVM or two smaller size QPP. And if we look at the complexity, as I mentioned that it is approximately 4 times faster than SVM. What does it mean? So it means that if you look at support vector machine algorithms, the complexity of usual SVM is not more than m cube. If we say m is the size of the training data. Okay, and since twin support vector machine, this solve two problems, that is in equation 1 and equation 2, which is roughly of size m by 2. Means we just assume that there are 50-50% class plus 1, class minus 1. Just make it balance, just assume it balance. So it is not always possible. Okay, that's why we are. I'm mentioning approximately 4 times faster, right? So we are just assuming that we have 50% of class plus 1 points and 50% of class minus 1 data points. So, and in this case, twin support vector machines solve two smaller problems of size roughly m by 2. So if you look at the ratio of SVM and twin SVM, so m cube upon 2 times m by 2 whole cube, so it is nothing but it is now 4, right? So now this is the dual formulation. I already tried to explain how to find out the dual formulation. Means we just write the Lagrangian functions, take the partial order derivative, KKT conditions, then you put it, and then you will get it. This 3 and 4. Okay. I hope you can do just make the Lagrangian functions and write the KKT necessary and sufficient optimality conditions, and then you solve it. So you will get 3 and 4 just dual problem. So, and finally you will get the solutions. This is W plus B plus W minus B minus. So essentially the matrices appear in the dual formulation 3 and 4 are not always invertible. So what we do, because it is possible that it may not be well conditioned in some situations. So on the lines of the regularization term introduced in ridge regression approaches, so they also introduce a regularization term, that is some delta I, to take care of problems due to possible ill conditioning of the matrices H transpose H and G transpose G. Okay. Now further, to move ahead, I'll discuss the least square twin SPM formulation. So here, least square twin SPM is one of the good formulation in the sense that it's a least square version, and it is simply solving system of linear equations, unlike solving QPP in twin SPM. And the third is we are not using any kind of optimization toolbox like LeanProg, QuadProg and all. Nothing. We are just solving system of linear equations. So how we write this mathematically? So you can see in phi and 6 and how it is different from the previous algorithm. So the only two major difference here, we are just introducing two norm in place of one norm of the slack variable, that is xi. Rather than writing C1 xi, so we are just writing C1 xi1 transpose xi1. That is two norm. Second is we are just replacing inequality constant with the equality of phi and 6. These are the two major difference, and obviously since we are considering two norm of the slack variables, so that the bounding conditions on xi1 and xi2 greater than or equal to 0, it will automatically redundant, or xi or eta, whatever. Okay, so now I'm moving ahead. It's very interesting problem, improved twin SPM. So it is a kind of first attempt towards the proposing few ideas recently. So this is improved twin SPM. What exactly they did it? This paper published in Science China Maths by a group Tan et al. So, advantages of ITSVM is first that ITSVM reformulates the primal form of TSVM to make it feasible for large scale data. Okay, and it also minimizes the structural risk, which results in improved generalization performance of the model. And the third, which is very important, this idea avoids the computation of the matrix inverses, while as a given other baseline models, they need to calculate the inverse of the matrices. So that infeasible, those baseline models are infeasible for the large scale data. And the last advantage is ITSVM doesn't have to deal with kernel generated surfaces, unlike the other given baseline models. So they are directly incorporate kernel brick in the dual problem. So it's very interesting problem. So I inspired with this formulation and developed a few. Okay, this is non-linear formulation in the same theme. So we'll move up. Okay, I'll move here. So this is large scale least square Venus view. So this work already publicly available it was published in IEEE transaction ACM transactions on internet technology. So from my team in 2021. So what we did here. So most of the twin SVM based algorithms like TD-SVM, twin bounded SVM, robust energy based least square twin SVM, or robust reduced universal twin SVM for class imbalance learning. So there are several other baseline models, just a few I mentioned here. So they suffer for the two main issues. The first is competing inverse matrices, which may lead to suboptimal solutions in some cases and make them a suited model for larger scale data. So this is one of the major issues and major advantages of the proposed idea. And the second is they employ kernel generated surfaces for the nonlinear case. Okay, these are two major issues usually in the baseline models. So, and the proposed idea is nothing but it is a least square version of twin bounded SPM that work for large scale data. How? So this proposed idea, LS-LSTSVM, searches for a pair of non-parallel hyperplane for classifying the sample. So by introducing different Lagrangian functions, it's very important here, this line. By introducing different Lagrangian functions, we obtain pair of unconstrained dual optimization problem. How? You see, and 27 and 28. So what we see, this is essentially uh, kind of least square of the TBS-BM problem. Okay. we just replace with inequality with the equality, least square, and introducing extra regularization term similar to TBSVM, and then we solve it. How to solve it? So as I explained that we are just considering different Lagrangian function. So it's very important. So those are interested in research, so they can just consider as a benchmark, and you can write a paper in any variant of the twin SVM on the same line. So if you look at the comparison and all data sets, codes, so all are publicly available in my GitHub repository. So you just need to search out mtanveer1 in GitHub, so you will get it. So we just introduce different Lagrangian functions, and then take the partial order derivative, this KKT necessary sufficient conditions. We solve it, and you can see in 35 W1 B1. So you see that invertibility issues are not there. So we do not need to calculate any inverse of the matrices. Okay. Similarly, for the second column W2B2, you can see here in 38. And in the same manner, you can look at 36, the dual problem. Here we have matrix Q cap, so there is no invertibility issues. So in that case, this formulation works very well for the large scale data. So these are just the way that we just predict with the help of this decision function, that's absolute of x transpose W plus B, perpendicular distance of x from the plane. So due to the least squares formulation and the extra variable in the Lagrangian function, the dual formulation has nothing to do with inverse matrices. Moreover, the dual is an unconstrained optimization problem which consumes less effort to get the solution. Any questions so far? Feel free to ask me any question. I'm happy to answer. Otherwise, I can move ahead and discuss the nonlinear part of this formulation. Okay, no problem, I can proceed. So in the nonlinear case of this formulation, it is entirely different from the nonlinear case of the baseline models of twin SVM. That is called TBSVM, RLSTSVM, and other variant of twin SVM. So we are just instead of considering kernel generated surfaces, we are directly introducing kernel function. So it means that you can see, rather than writing this KA, this transpose, so we are just writing phi A. In place of A, we are just replacing phi A or phi B in 42 and 43. So, and if you look, when we solve it, the dual, you can see that we can directly solve it, and finally we got 45, 44, 45. And finally we get the problem. Okay, so let me try to show you a few results. So yeah, so can you see these results? Anyone?
Yes, sir. Now better.
Okay. So you can see that I have this first three columns: TBSVM, TWSVM, RELS, TWSVM. So these are the baseline twin SVM variants, and the last column is the proposed idea. So you can see that average rank is lowest. Overall wind tie loss is also better for the proposed idea. So since we are dealing for the large scale data, so I just show that what is the performance for the smaller size data. So we see here that smaller size data, the proposed idea performing well. Okay, you see here the same case. So, but now this is the formula. This is the main implementation when we are dealing for the large scale data. You see that we are when we are considering connect for mini bone data, so you see that the baseline approach is failed after some size of the data, but the proposed idea, the last column, that is performing well. Another another point to be noted here, when you see uh, for example magic data. In the magic data, if you look at the time, so for the time for the purpose is very less, just 15 seconds. But if you look at the baseline, so it is 284 second, 260 second, 267 second. So it's a big difference. So I think a lot of experimental results are available in the paper, in the whole manuscript. So I would like to suggest you to just go through the main original paper, largest scale least square twin SVM. This is in ACM transactions on internet technology. You will get it. I think full text is available on ResearchGate. You can find out easily once you Google it. Okay. Now, this is the second approach, a large scale pinball twin support reactor machine. So, this work is still not we are not getting acceptance. So, this paper is under the revision in one of the top journal called Machine Learning in Springer. So we already got the positive review, positive feedback. So we just resubmitted the revision. So it's very interesting. So what we did in this formulation, that there are people already have introduced pinball loss, SVM pinball loss, twin SVM. So means in this case, what we are doing, will explain point wise, but in a line, I can say that this proposed idea is effective for the noisy data, for the larger scale data, and for showing the more robustness. So let me now try to explain point wise. So in order to make the model formulation suitable for larger scale data sets, we formulate the problem such as the first, merits of both TBSVM and pinned GTSVM are retained while ignoring the calculation of the large matrix inverses. These changes are the introduction of a regularization term and the addition of the inequality constraint. Since pinball loss is already present in the primal problem of pin GTSVM, So LPTWSM is insensitive to noise and is more stable for resampling. The third, the proposed idea ignore the computation of large matrices inverses, leading to the applicability of the proposed idea to the larger scale problem. And the fourth, the proposed approach allow for the kernel trick to be incorporated directly into the dual problem instead of kernel generated surfaces. And the last is the proposed approach possesses the SRM principle, unlike pin GTS-VM, which gives the formulation the possibility of obtaining better generalization performance. Almost all the data set, most of the data sets, and it means that the proposed formulation stands as a significant improvement over the baseline approaches. Yeah. Just 5 more minutes. I need to wind up. Okay. Okay. So let me just try to give. Okay. Overall idea is the same. So let me just try to show you some background and some information. Yeah. So some of the these are some activities at IIT Indore in my research lab. So these are some research projects uh, going on in my lab. I think one project is already completed, Early Career Research Award. So rest are undergoing. So if any of you are interested to work in any of these projects, so you are welcome to just drop me an email, okay, and then we can discuss more. If you have any background related to any of these projects, okay. So now I would like to acknowledge the funding agencies, uh, different funding agencies to support my work. So this is just an invitation to submit your high quality work in these special issues of the first one is IEEE Journal of Biomedical and Health Informatics. So it is one of the most premium journal in biomedical engineering. Impact factor is 5.22. So if your work is related to the theme, that is advanced machine learning algorithms for biomedical data and imaging, then you are welcome to submit by the deadline. Second is also in one of the top journal called Annals of OR, Spring. Uh, the theme is robust data analysis and its applications. And the third special issue is advanced signal acquisition and processing for Internet of Medical Things. This is in CMC. So this is also good journal, open access, but with impact factor you can see is very high. Okay, so now I would like to invite you in MISP 2021. We were the founding organizer of this conference at IIT Indore. Later on, it was organized at IIT Allahabad, and this time organizing by NIT Arunachal Pradesh, Dr. Deepak Gupta. We are just founding chair, so I welcome you to join the conference during September 23 to 25. So I think if you want to just join as a participant, you are welcome to register. Okay, so this is Iconic for 2021. So it's also a very good conference. This is Core Rank A conference. It will be in Bali, Indonesia. I'm one of the publicity chair. So, and the last date of paper submission is June 30. So we have 1.5 months more to submit the manuscript. And this is an announcement for ICONIP 2022. So it will held in India. I'm one of the main journal chair of this conference. So you are welcome to submit your papers and help me for the organization. If any of you are interested, you can drop an email to us. Okay, so these are just some of the references. Thank you very much for your attention. So, for if you want to contact me, you just contact me via email mtanveer@iiti.ac.in. Thank you. Thank you.
The next session handed over by Ailaya Kavati, Assistant Professor, Department of Computer Science and Engineering, NIT Warangal. He emphasized on regression analysis using Python. The next session handled by Ms. Divyasri S, Managing Partner, OpenFine Innovations Lab, and she emphasized on Introduction to Python Programming Language. The next session handled over by Dr. Ramalinga Swami Cheruku, Assistant Professor, CSE Department, NIT Warangal. He emphasized on artificial neural networks and its applications for diabetics classification. The next session took over by Ms. Divyasri, yes, and the topic emphasized was types of machine learning systems. The next session handed over by Ms. Divyasri, yes, which was a hands-on session in Python. Another session by Ms. Divyasri, it was end-to-end machine learning project and hands-on session on how to execute a machine learning project. So on the next session, Colonel B. Venkat, Director Faculty Development Cell, AICT Delhi, emphasized on national education policy. Dr. M. Tanveer in the next session, who is an Associate Professor and Ramanujan Fellow Discipline of Mathematics, IIT Indore, emphasized on large-scale support vector machine algorithms. In the next session, Dr. Ravikumar Jetto, Associate Professor, EC Department, NIT Warangal, emphasized on multiple linear regression and chlorophyll estimation. The next session handled by Dr. Ramalinga Swami Cheruku, Assistant Professor, CSE, who emphasized on classification rule mining for diabetes classification. The next session followed by Dr. Konda Reddy Mopuri, Visiting Faculty, Computer Science, IIT Tirupati. He emphasized on fooling the intelligent machines. And the next session handled by the same Professor Kondareddy Mopuri on the same emphasis, which is fooling the intelligent systems. The next session handed over by Dr. K.G. Srinivas, Professor, National Institute of Technical Teachers Training and Research, NITTT or Chandigarh. He emphasized on pedagogy for engineering educations. All the participants from various universities and colleges expressed their gratitude to staff of the Department of ECE SRIT for creating awareness on machine learning recent trends and applications. So now I would like to invite Dr. G. Balakrishna sir, Principal SRIT, to speak few words on this occasion.
Yeah. Thank you, others. But before going to listen from us, it is better to hear from the participants. What is their feedback and what is their
Sure.
experience in attending this one? So yes, I request all the participants, at
Sure,
least
sir.
few participants, they can
Yeah. Sure, sir.
a few participants they can share their experience and feedback on this STTP. I request.
Sure, sir. Sure, sir. So
So any of the participants, faculty participants, you please come forward and give your valuable feedback so that we can conduct more effectively if anything has gone wrong in this STTP.
Yeah, good afternoon, sir.
Yeah, sir. Good afternoon, sir, please.
This is Dr. B.S. Panda from Visakhapatnam.
Right, sir.
sir, please
Yeah,
go
thank
ahead,
you,
sir.
Yeah, thank you, sir. Very nice STTP, really. In this pandemic area, really the resource persons and the valuable experience they are shared with us. And they're given the resources, notes, everything value for us. So really it is very good and very nice and effective, sir. And the management of SRIT and all the coordinators are thankful to you and thank you, sir. Thank you very much.
Thank you, sir.
Good afternoon, sir. Hello.
Good afternoon,
Good
Srinivasa Rao, sir. Good afternoon, Srinivasa Rao, sir. You please speak
Ah,
a few
sir,
words.
I am Srinivasa from Vishnu Engineering College, Bhimavaram, sir.
Okay, sir.
Okay, so
Please. Yeah.
it's a good workshop, sir. Really, in the last 6 days, myself participated actively. So NIT Warangal professors delivered good lectures, which are very useful. So nowadays for ECE also, this type of machine learning concepts are very much important. So really, it's very useful to me personally. I thank the SIT management to conduct this workshop. Thank you, sir.
Thank you, sir.
Hello.
So,
Hello. Hello.
Yes, sir. Vishwakarma, sir. You please.
Dr. H.L. Vishwakarma, Professor, Government Engineering College, Jagdalpur, Chhattisgarh.
Yes, sir.
I have attended many conferences and FDP and sessions. So the FDP organized by SRIT was very unique. Congratulations on your creativity, resourcefulness, and useful ideas, strategies. Powerful, very powerful, exciting thumb up. I have been to entire FDP and not see so much unusual information in all 6 days as I did in these 6 days programs. Thank you, sir, for your very nice arrangement of FDP. Thank you, sir.
Thank
sir,
you, sir.
this is Kulai Swami here, sir.
Yes, sir. Please share your experience, sir.
I'm a research scholar, BITM Ballari, sir. First of all, I would like to extend my heartful congratulations to whole SRIT EC department for organizing this excellent STTP program, especially from the beginning of the day, that is the first day to the last day. Every second and everything is maintained properly and well organized, sir. And especially the resource persons are eminent and they have given more knowledge to us. I mean, for especially research scholars, where they need to start the research work and where they need to concentrate in research paper writing and all those things, sir. And from my side, A special thanks to the EC HOD sir Ravichandra sir and Deepthi madam sir, and special thanks to the Venkateshwar Rao sir who is organized. Thank you.
Hello, sir.
Thank you, sir.
Hello,
Thank you,
sir.
sir.
I am Hitesh Kumar Gupta, Assistant Professor in SRMS Engineering College, Bareilly, UP. So, sir, your program is very good, and you arrange the resource person is very well. So, congratulations, sir, for a completion of your program. Thank you.
Thank you. Thank you. Thank you, sir.
Good evening, sir.
Yes, Madam Rekha Bagil. Please go ahead, madam.
Yes, good evening, sir. My Rekha Patel from Galgotia College of Engineering Technology, Greater Noida, sir. Sir, I have attended many faculty development programs, but your faculty development program, that is machine learning, very good, sir. I have got so much knowledge from this FDP, sir. Congratulations to all the resource persons and all the faculty members of your department, sir. Thanks a lot for organizing this wonderful faculty development program, sir.
Thank you, madam. Thank you for your feedback. Any other participants? Please.
Yes. Good afternoon, sir. Am I
Dr.
audible?
Kabir. Yes, sir. Yes, sir. You are audible, sir. Please go ahead, sir. Hello. So there is a technical issue, it seems. Any other participant?
Good evening, sir.
Sir, yes, sir. Dhananjay, sir.
Congratulations, sir, for whole organizing the committee.
Thank you. Thank you, sir.
It was really wonderful.
Thank you, sir.
I have only one suggestion. That is you try to include the more industry part
Yes.
participation,
Praveen Kumar Shetty from
which is
Sambalpur
appreciable.
Sure, sir. We will look forward this point, sir. Sure, surely. Okay.
Thank you very much.
Thank you. Prabir Kumar Shetty, sir. You please share your experience. Oh. Yes. Any other participants who would like to share
C.
their
Anandan.
experience?
C. Anandan.
C. Anandan, sir. Yes, sir. Please.
Good
Please go
evening,
ahead,
sir. I'm Anandan, Assistant Professor from SRM TRP Engineering College, Trichy, sir. So the STTP was very excellent, excellently organized, sir. So we gained knowledge in ML. So all the professors, all the eminent professors gave many inputs to us. So it will be very useful to do our research work in this field. So thank you for the management for conducting such a STTP. So I thank the organizer, the coordinator. Then and there, he insists us to join because since it is in a pandemic, we are all in home. So SARS repeatedly keep on reminding us to join. So thank you, sir. Thank you so much, sir. Thank you, sir.
One more, Mr. Faninder has raised his hand earlier.
Yes, sir. Please, Faninder, sir. You please go ahead, sir. Faninder Electronics.
Good evening, one and all present here. My name is Fanindra Ravi, and I'm working as assistant professor in Sir Vishweshwara Institute of Technology, Bangalore. First of all, I would like to sincerely congratulate all the organizers for having put sincere efforts in bringing out this STTP of this form. 1 week conduction of STTP in this aspect is not an easy task. My wholehearted congratulations and sincere thanks to all the coordinators who are present here. And it was a wonderful session. People from NITs and IITs, really, they have explained very well the concepts. There are some topics which are really interesting to the present event. Sir, one sincere suggestion from my side, if you can include more of hands-on session, that would be really great instead of giving a lot of theory. So if as on date, see, we are faculty members, right? So we also understand the implicality of doing it with instead of seeing it. So if you can do it and see it, then probably the impact of this kind of workshops would definitely be quadrupled. So yeah, it's a small suggestion from my side. Thank you so much. Thank you all for conducting this wonderful session.
Thank you, sir. Thank you. So, any others?
Good evening, sir.
Good evening, madam. Anjani Devi, madam. Please go
Yes,
ahead,
sir.
madam.
This is Anjana Devi, Assistant Professor from Adiyaman Engineering College. Uh, this is from Tamil Nadu State, sir.
Right.
And I would like to extend my great thanks and congratulations to SRIT, uh, Principal Sir, Dean Sir, HOD Sir, and to all the coordinators who have done a superb job. Because as a assistant professor, I feel some difficulty in guiding my students for their projects. So now I have got some good and basic idea on machine learning and Python. So I can encourage my students and their future will be shaped a lot, sir. So I thank a lot because as we were student, we could not get the opportunity to learn Python and all. So it's a right time and platform to learn. And my big thanks to SRIT for providing this opportunity, sir. And and I'm expecting more and more program from your side, sir. For research oriented paper, we are looking for touch screen technology, sir. So it's my small request, if possible, to conduct some program on touch screen technology, sir. So it will be very helpful, sir.
Sure, madam. Your
Thank you.
input
Thank you
is
so much,
recorded.
sir.
Yeah, thank you, ma'am.
Yeah, thank you so much, sir.
Any others?
Yes, sir. Myself, Motilal from Engineering College, Jhalawar, sir.
Yes, please, sir. Please.
Sir, so much thank you for organized team. Organize a very good FDP. I would like to, in future, I will also much more, everybody will be attendant and some lot of informative learning have learned in this FDP. And again, I wish so much thank you for good organizer team. Okay, thank you, sir.
Thank you, sir. Thank you. Any others would like to share their experience? Please come forward.
Sir, good evening, sir. This is Dr. Mahadev Swami from Vidyavardhaka College of Engineering, Mysore, Karnataka.
Yes, sir. Yes, sir.
Sir, the FDP was very well organized, sir. I wholeheartedly thank the management of SRIT, principal and HOD of ENC department and all the faculty members and all the organizing teams. Sir. Thank you so much, sir.
Thank you, sir. So, any other participants? If you would like to share your views on the experience you have on your FDP, online FDP, please come forward. So
Good
now
evening.
yeah. Yes, madam, please, you go ahead.
Good evening, sir. Myself, Sujata from CSC Department, SRIT itself. I'm very much thankful to the EC department, sir, especially. So
Thank
I
you,
don't
madam.
know anything about machine learning, sir, as I'm fresher to this college also. But I have learned many things from this FDP, sir. Very thanks to everyone, sir. Thank you so much.
Thank you, madam. Thank you. So now I would request Dean Academics, Dr. V. Shankar, sir, please share your views on this FDP, sir.
Yeah, thank you.
Thank you, sir.
At the outset, I welcome you all to the valedictory session. And it's my privilege to be associated with this valedictory session. And basically, I'm a retired professor from JNTU and joined SRIT last year. And I'm happy that now this is first EC department STTP sanctioned to EC department on machine learning its applications by AICTE. Earlier, civil department, mechanical department have conducted. By Monday, we are conducting for computer science department also on cyber security and blockchain technologies. That is 2 weeks FDP. So So on behalf of the SRIT, I welcome you all and inform all the concerns. So it is again multidisciplinary area, and everyone may be interested in joining in that cyber security and blockchain technology and applications. So that is 2 weeks program. 17th morning inauguration will be there, and I request all the coordinators to share the information of the STDP, FDP of the CSC department of our institution to be conducted on 17th to all the participants. So brochure will be sent to you. All the faculty will be receiving by today evening, hopefully. And I request the concerned coordinators to send it to all the participants here. They may be interested. If they are busy, they can inform their colleagues from the respective colleges, because participation is there from all parts of the country. I understand. And I am really very happy on various issues. Consistently, people have been attending in good number. And we are highly grateful to our AICTE FDP director, who has been always keen in either orient or driving himself to make the other people to be given orientation. He has been always keen in attending to the inaugural sessions, and then various opportunity when he takes to give on national education policy. No effort is going to be wasted by him. I have observed him in many of these things, and also I am very happy about the participation that is made by the participants, giving the feedback also. Very enthusiastic in giving the feedback also. I am very happy to know. Definitely hands-on session, 1 or 2 already have been made. And we definitely go through it, because these FDPs or STTPs, 1 week short-term training program is 1 week. FDP is 2 weeks program as per the AICTE terminology. So this STTP will be augmented with, because this is phase 1 only, it will be augmented with some more phase 2 and 3 or 4, depending on the budget that is being sanctioned and allocated based on the permission that is going to be given. So in the upcoming this one, we are going to have phase 2 subsequently, which will be announced by the coordinator subsequently. And really some interesting sessions have been made by the participants on the new areas and also industry participation. Definitely, even the first inaugural session was done by Dr. Narayan. He has given very simple definitions and understanding of various fundamental concepts of the artificial intelligence, machine learning, deep learning, and also data science. And we are happy to announce from our institution that data science and artificial machine learning have been initiated this academic year. That is already first year students have joined. So that is where we understand the importance of the new technologies, and then they are of highly interdisciplinary nature. Everywhere, core faculty, all people think that core department people may not have the interest in this, but all these advanced technologies have to be learned to the core applications. That is where basically, although I am from EEE, I am always keen in attending to these programs whenever the time permits. And also another, of course, the resource persons have given excellent presentation, and also the resource person from NITTR, Professor KG Srinivasa, he has been always keen in giving pedagogical training or even on the new education policy. Earlier also in other STTPs conducted by SRIT, who has been always associated with us from NITTR Chandigarh. I know he's this one, although I missed yesterday to listen to his lecture. So I know his presentation. Earlier also I listened to his topics. So like that, of course, every individual I may not be able to acknowledge here, but I'm very happy that the STDP has gone very well progressed in spite of the difficulties that have been faced by the participants and organizers, as well as the research persons in this pandemic situation. Still, we could manage to arrange all the lectures without any disruption or without any discontinuation. I'm really I'm really thankful or grateful to all the research persons also who have adjusted themselves to the research persons' difficulties, and then engaged their sessions either in advance or later by adjusting with the research persons' difficulties. So this first of its kind, although in pandemic situation we are going with online classes, still online during the pandemic period when the resource persons themselves are unable to deliver, the other resource persons have adjusted their classwork. This happens only in the institutional environment, but even in the national level, people have adjusted to the correspondingly with respect to the organizing these sessions. And also, I'm happy in spite of the troubles faced by the faculty themselves in the organizing from the Department of SRIT, ECE also. People have arranged these things. A lot of pains have been taken. It is first of its kind. Really, highly people are committed, and that is where the STTP has been progress. I'm not just saying because I'm an SRIT. I observed that there is a lot of commitment in spite of the several difficulties. We have been contacting together and then arranging these sessions without interruption. So I thank the management of the SRIT, Chairperson Dr. J. Padmavati Garu, and correspondent Sri Allur Samshiva Reddy Garu, and patron Dr. M. Ranjit Reddy Garu, and the principal, who have been always cooperative with us, and all the faculty. I really appreciate their consent, and large number of participants consistently have appeared for this particular program. So I thank very much once again the authorities for giving this opportunity. Thank you all.
Thank you, sir.
Yeah, over to you.
So now I am honored to invite Dr. G. Balakrishna, sir, Principal SRIT, to speak at this event.
Yeah, thank you,
Over to you,
Adarsh.
sir.
Thank you, Adarsh. Thank you. Is my voice audible, Adarsh?
Yes, sir. Yes, sir. It's clearly audible, sir.
Yeah. Thank you once again. Respected Professor V. Shankar, sir, Dean of Academics, SRIT, coordinator of this program, Dr. M.L. Ravichandra, head of the department, ECE, and in charge head of the department, Deepthi Madam, and coordinators of this program, Adarsh and Venkateswar Rao, sir, technical committee, organization committee, and all other faculty participants. Very good evening to one and all. And it's really very happy to listen all of you regarding this STTP. So it's it's difficult to speak at the last because all the points have been covered by all the participants as well as our Shankar sir also. So it's very difficult. Of course, I too have some more points. Okay, it's on this occasion I congratulate and appreciate the efforts of this coordinator and technical committee, organizing committee of this SCTP. I hope all the faculty participants, they have learned much about this machine learning and recent trends and applications, and I sincerely request all the faculty members who have learned so many things about this machine learning and recent trends and applications. This knowledge which have been gained through STTP can be shared to your students also. That means it is very much essential. That means the AICT is insisting to conduct STTPs to gain the to train the faculty members. Subsequently, they will train the students. That is the main motto of conducting these type of STTPs or FDPs. So I sincerely request all the faculty members to share the knowledge that you have gained through STTP here to your students. Okay, so it is my request. And at the same time, I sincerely thank the AICT for sponsoring this STTP, and we have two more STTPs in pipeline on the same topic, machine learning and recent trends. And I request all the participants to definitely take the opportunity in attending that phase 2 and phase 3 of this kind also. And at the same time, as Shankar sir mentioned, we have been conducting one more FDP from CSC department. Immediately after this voluntary function, we will post the information regarding that FDP in the WhatsApp group itself. No issues. If possible, you just inform all the faculty members of your knowings and take a part of that one also. And as suggested by some faculty participants, definitely we will include hands-on session in the subsequent sections if possible. Okay, and at the same time, we will invite more persons from industry also. Of course, here also we have a few resource persons are from industry also, it seems to be. Anyway, we will increase that number next time, and we will include hands-on session as per the what you call as whenever it is possible. It's okay. And as the instructions given by the All India Council for Technical Education, we have included the national education policy as well as pedagogical initiatives also, because most of the participants here are faculty from various engineering colleges, it seems to be. And it is very much essential to know what is the latest what you call as moderations that is happening in the technical education throughout the India, and what are the initiatives of AICTE, all those things. I hope we have gained that knowledge. What are the initiatives of AICTE through national education policy? Okay. And at the same time, we have included pedagogical initiatives also. What is the various pedagogy which can make the students very interactive with the faculty members during their delivery sessions in the classrooms, in the online or offline. Okay, so and at the same time, it's very happy to hear from the participants that the participants are from different parts of the country. So Tamil Nadu, Karnataka, it's very happy. It's really happy. Okay, so I once again thank the management, because SRIT is always SRIT management, our dynamic Samaseva Reddy sir will always be behind us and encourages us in conducting these type of workshops, without which it is not possible actually. I sincerely thank Padmavati madam also, and Ranjit Reddy, who is the driving force of SRIT. And once again, I thank everyone. Uh, I thank every participant also. Okay. Thank you very much. Thank you very much for giving this opportunity.
Thank you, sir. Thank you for your valuable inputs. Definitely, we will have a follow-up in future. Thank you, sir.
Right.
So,
And
so
really,
now,
and one more thing. I have two faculty members here. Actually, Kulaswamy is there. Actually, Kulaswamy, you
yeah.
belongs to Intel Medical earlier. Yeah, yeah.
Sir,
Kulaswamy, how are you?
good evening, sir. Good evening, sir.
Good evening.
How are you
And
doing?
yeah, yeah. How are you, Kulaswamy? You're fine.
Sir, fine, sir. Thank you, sir. Thank
Yeah, Paramesh Naik also I have seen somewhere.
you. Yes, sir. Yes, sir.
Yeah, yeah.
So it's a good,
It's very,
good STTP, sir. It's very useful to us, sir. And
yeah, yeah.
once again,
Thank you,
I'm
thank
very
you.
thankful to the SRIT management and EC department and Dean Academics and Principal sir and everyone, sir.
Yeah,
Yeah,
it's
yeah, yeah.
happy.
In future also, we'll participate in session 2 and 3 also, sir. Not a,
Yeah, sure. It is required. Yeah, and
Sir,
it's
thank
very
you very
happy
much,
to.
sir.
Parmesh, how are you?
Sir, thank you very much for conducting such a STB, sir. Sir, our guide is Ravichandra sir. He has
Oh,
suggested, sir. Okay.
right. Okay, so in phase two,
Okay,
phase
thank you,
three
sir.
also, you just join with us. Okay.
Yes,
So
I
it's
sir.
it's very happy to see Parmesh Naik and Kulaswamy. These are all two faculty members who have been who have worked together earlier at Intel Engineering College. It's happy to meet them on this occasion. It's happy.
we also, sir. Thank you, sir.
Thank you, sir.
After
Right,
a
Thank you,
long
sir.
time, we are
Thank you,
hearing your words.
thank you very much. Thank you very much. Anything else from Adarsh or
thank
coordinators?
you, sir.
Please go ahead.
Thank you, sir. Thank you, sir.
Right.
So
Thank you so
now
much.
it's now it's the time for the voice that we have been waiting for. That is vote of thanks, which is read by K. Venkateswar Rao sir, who stood the backbone of this program actually.
Yeah. Really, we had to appreciate. Yes. So of course, we have Mr. Ram Reddy also. Ram Reddy also has completely
Yes, sir.
extended their support in conducting this. Yes.
Yes, sir.
I
Yes, sir.
yes.
Even up to just before starting also, I have been in touch with him. I thought he will be attending. Somehow we missed him.
Ram Reddy is not there here.
No,
No.
sir. He has not joined. It seems, sir.
Right. But he has
But
extended.
yes,
Sir, he
also
joined and left,
arranged.
sir. Sir was
Yes, sir.
joined and
Maybe
left, sir, due to
Yes, sir.
network
maybe
He
issues.
gave
network
us.
issue is there.
Maybe.
Maybe network
Yes,
issue is
sir.
there. Yeah.
He
Yeah.
joined for a few minutes and he left, sir.
Yeah.
Okay.
Okay.
So you just go ahead with the what of
Sir,
thanks.
Yes, sir. Sir, Deepthi madam from EC department in charge HOD would like to share
sir,
her
Yeah,
views
please,
on this.
sir,
please, go ahead.
sir, good evening,
Please.
sir. Good evening, all,
Good
to
one.
all the participants. I should appreciate the work of Venkateshwar Rao sir and Adarsh.
Thank you,
They
madam.
really did a very good job, um, and thank all the participants. And I just want to congratulate these two people from EC department. Thank you, sir.
Thank you, madam. It's I believe it's a collective effort, and we took inputs from the whole department and shaped this FDP on their valuable inputs. Thank you, ma'am. Thank you. So now it's over to you, Venkateswar Rao sir. We have been waiting for you, your voice. It's time for vote of thanks. Thanks, sir. Go ahead, sir. Thank you, sir. Venkatesh, sir. I thank all the participants, and we will meet again in the next phase of FTP.
Yeah, yeah.
Thank you, one and all.
Thank you very
Thank
much.
you, one and all.
Yeah, thank you. Stay safe and stay promoted. Thank you. Bye.
Sir, it says we need permission. Venkateshwar, sir, it says it needs permission.
Yeah, Mr. Fanindra, you want to speak?
No, sir. That the overall feedback form, there was permission issues. That's what I wanted to tell you.
Yeah. That's what we are looking into. Yeah, somebody's already pointed out that. Yeah, we are just looking into that. Venkateswara garu? If everything is over, we can close the session.